welcome everybody. Welcome back. And I have a few announcements. So maybe let me start, see if there's any questions. Anybody had anything they needed help with from yesterday, or any specific questions before I go on with my announcements?
Hi, Mohammed. I have a question.
Yes.
I have how to change. It's a very basic question. Maybe you said in the beginning yesterday, but I was late. So how to change directory to go to the material, to upload the material and then set the directory to get started.
Yes. Are you using the desktop or the cloud version of Pumas?
So I'm using the coupon which you sent me.
Okay, so that would be the cloud. Yes. So what you need to do is, let me share my screen and show you. Can you see my screen?
Yes.
Yeah, so what you need to do first is download this. So go to this Git repository here, which is where the workshop material is, or GitHub repository. And then you would need to download it as a zip file. And after you do that,
I have done these steps. So I access the Julia Hub, but then
yes.
How to upload the material and set the directory.
Right. So the first step is you need to upload the zip file to Julia Hub by drag and drop. So you would drag and drop it into the left pane here. So Julia Hub should look something like this for you. So you can drag the file and drop it here in this pane here. And then it would show up on the left-hand side. That would be the first step. So can you try that?
Okay, so this should be drag and drop to the left side, right?
Correct, to where the folders and files are. Yes.
Okay. I will do it now.
Okay, and then once you do that, you would need to go to the command palette of Julia Hub, or of VS Code rather, and you can do this with Command Shift P or Control Shift P. If you're on a Mac, it's Command Shift. If it's Windows, then Control Shift, and then you can just write terminal and go to create a new terminal, and this should launch a new terminal at the bottom here, and that in this terminal you should be able to, like if you do ls, for example, you should be able to see the zip file that you just uploaded. So the terminal should take you to the sort of top level folder here. And so if you do ls, it should give you or show you the zip file. Then the next step is to unzip this file using the unzip command. And so you can write unzip and then the file name .zip, and then that should unzip this file. And then you should have the folder accessible there directly. Then once you have the folder on your, like once you unzip the file, it will be, let's say, a folder like this one. You can right click on the folder and then change to this directory. So this is how you can change. Alternatively, you can just call cd from the terminal, cd, and then change to the folder which has the same name as the zip file, or would have the same name as the zip file. And so it's a multi-step process. The first step, as I said, is to download the zip file, then to drag and drop it to the left-hand side. And then you need to open a terminal. And then you need to unzip the file from the terminal using the unzip command. And then once you unzip the file, you should be able to see the folder on the left-hand side. And then you can right-click this folder and change to this directory. Or you can change the directory directly from the terminal by using the cd command followed by the name of the directory.
Thank you.
Of course, hopefully that worked. Good. So that was actually one of the things I wanted to cover today. So anything else beside this this point or this question? Anybody else has any questions from yesterday? All right, so let me start with my first announcement here, which is that we, so I remember yesterday, some people were curious about machine learning. And so and I mentioned that this workshop is not really dedicated to machine learning per se, but we might touch upon it. But we also have a dedicated workshop to machine learning and nonlinear mixed effects modeling in drug development that's happening in April in Basel, Switzerland. So perhaps not too far from some of you. And so if you're interested in a full workshop, essentially dedicated to this topic, that in some way assumes some knowledge of Pumas, we will probably spend 1 or 2 days on basic, or maybe just 1 day on Pumas, just to cover the basics. But if you want to attend, for example, just the machine learning part, you could try maybe sending me an email, and I can try to connect you to the right people who can manage this. But that's a much more dedicated workshop. And the way you can find this is if you go to our homepage and then browse events, and then it's a little bit hidden down there. If you go down, you'll see there it is. It's this one, April 7, 2025. And if you click on read more, you can see more about the details of the workshop here. So that's the first announcement. The second is that we have Pumas 2.6.1 coming up soon, or coming released soon. In this workshop, we're using 2.6.0, but 2.6.1 has a lot of really nice bug fixes that might be necessary to get as soon as, or nice to get as soon as it comes out. So this should be coming out soon. And also coming out soon is hopefully a DeepPumas desktop version. So far we've had only DeepPumas on the cloud. But the hope is that we can also release the DeepPumas desktop version in the next couple of months. And that way academics can also get their hands on it for free, basically, and be able to do some interesting research with machine learning and nonlinear mixed effects modeling. Another sort of announcement was something I forgot to mention yesterday, is that actually when I installed the Pumas desktop, I noticed that it was not using all of the threads or multiple threads on your machine by default. And so this should be fixed in the next deployment of Pumas. But for now, the way to change it is actually an opportunity also to teach how to customize these settings. And so if you go to the command palette here, and then you just write settings, you'll see that this preferences open user settings. So if you go to user settings, you'll see these are all settings associated with the Julia extension that basically when you install Pumas, it sort of tries to hijack your Julia extension and set up all these default environment variables and options for you. And so in this case, what you want to look at is this additional arguments. And what I did is I added some, so in your case, let me maybe close this to give me more space. In your case, you probably only have this first argument here as an additional argument. If you want to use multiple threads by default, you would need to add another additional argument here, which is a string with the hyphen T and then the number of threads. I just use 5 because that usually works for me. I have 4 that can do compute and 1 that can still do some displaying and so on. But this is hopefully going to be fixed in the next release of the Pumas desktop. Good. Yes. So yeah, if you go to the end of this Julia additional args, you can add this additional argument here and write whatever number of threads you would like to use here. And that should take care of this. You would also need to restart your Julia. And so if you want, you can just, so I did mention how you can kill Julia, the Julia session, but basically this bin or trash can is how you kill a terminal. So you can go to the Julia REPL and then kill it like this. And then you can go back to the command palette here and write Julia start, and then you should be able to see how to like this Julia start REPL. And if you click it, it should start a new REPL with the correct options this time, which is the number of threads. So let me go back here. Now, let's say you started Julia after changing the number of threads. The way to confirm that the number of threads is correct is using this threads.endthreads function, which should give you the correct number of threads that you chose in the options. In this case, I chose 5, and so it's giving me 5 threads. So that's how you can confirm this. Again, hopefully this should all be done by default or fixed by default in the next version. Good. So let's move on. So yesterday we stopped at defining models essentially, and right before fitting the model. So let me just revisit the agenda for today. So the agenda for today, we're supposed to cover diagnostics, metrics, and plots. and together with estimation from yesterday, some non-Gaussian random effects, how to rewrite your model to take advantage of these non-Gaussian random effects, how to do uncertainty quantification and your population parameters using things like Bootstrap and so on, and then simulation prediction and some introduction to Bayesian estimation. So that's hopefully the plan for today. Good. So to recap, yesterday we defined this model here, and this model had some population parameters in the param block, had some random effects or subject-specific parameters for each subject in the random block. The covariates were declared in this covariates block, and then all the sort of staging of the parameters, combining covariates with population parameters with random effects, was all done in this pre-block here. And then the dose modification parameters like lags and so on, they were all defined in this dose control block. The initial conditions of the dynamics were defined in the init block, and the dynamics were defined in this dynamics and vars block. So the vars block defined these shortcuts that we could reuse in different places, and then the dynamics only defines the rate of change of the different compartments using any arbitrary, essentially Julia code on the right-hand side here that you can write. And there was a question yesterday about the macro approach of defining models versus the functional API. The nice thing about the Pumas model macro is that you have access to the entirety of the Julia language, essentially, and you can take advantage of it here. For example, in this pre-block, you can use any function. I can import a library for machine learning, for example, and use a neural network here if I want to. And actually, that's one of that's sort of how it enabled us to build this DeepPumas product by integrating all these different packages together directly into the Pumas model macro here. And so even though it's a macro, but it still doesn't take away a lot of the flexibilities that you have by having access to the entirety of the Julia language. And you can define functions outside of the model and then reuse it here. And you can use it in the pre-block, you can use it in dynamics, you can use it in the derived block as well. So it's really quite flexible. Good. So let me, because I just restarted Julia, I need to rerun these lines here again. So let me just rerun them quickly. And this here is the model definition. Just like yesterday, if you have any question, please unmute yourself and interrupt. Now, I did also mention yesterday that in Julia, when you call a function the first time, typically takes a little bit of time to compile, because the function is actually compiled for every combination of inputs to give you the fastest code, basically, that can run. In this case, we have the model description. I think I showed this yesterday. So here it tries to display all the comments essentially that you're writing here. It will be displayed here. So it will be a dictionary for all of these comments that you wrote here. And then we have the laticify function, which allows you to build a lattice representation. So that's a lattice representation of your dynamics, or you can choose different blocks here as well. So you can build a lattice representation of each block, essentially. And this is also possible because of the macro approach that allows us to do this quite easily. And then you can then render this lattice. Let's do it for the dynamics. You can render this lattice or laticify output to take a look at the math form of the equations, which is often useful when debugging to make sure you haven't made any coding mistake and that everything looks normal. So that's also pretty good. Now, let's say you already defined your model and we had already read the population from a data frame into a Pumas population. And recall that a Pumas population is just an array. So if I do the type of this here, it's just a vector of subjects, essentially. And I mentioned that usually you're interested in the first maybe type here and the first type parameter, but maybe the rest are not too important. So this is just a vector of subjects. Because it's a vector, it works like any other vector. I can select one element of it. I can subset, take the first two elements and get another subpopulation, essentially, here, and I can use it like any other vector. So this is the second argument. And then the third argument is basically the initial parameters. So where you want to initialize the fit. And so we have this, if you remember in your model, we actually defined some initial parameter values for some of these parameters. And for some, even if you don't define it, it will just be taking the default value. So if it's a positive parameter, the default value will be 1, for example. But because we did define initial values, then these initial values will be stored in the model. And then when you call init params on the model, it will output these initial values for you. So if you go down here and call the init params function, it actually outputs all the initial values that we hard-coded directly into the model. And this here is what we call a name tuple. So maybe briefly yesterday I discussed name tuples when I confused them for the begin-end block with parentheses. But a name tuple is just like a regular tuple. So regular tuple has like values that can be different types. The name tuple is very similar, but it allows you to put names on each value. So now the first value will be associated with this name N1. The second value will be associated with the name N2, and the third value with name N3. And so if I define this is a name tuple now, I can now access the values either by index like this or by like the field name here directly with the dot notation. So I can do dot N1 like this, or I can also access it with this notation here as well. So there's different ways to access each element. And so it works like a tuple, but it also works like a sort of a dictionary, like here, where you can access the keys with these symbol keys. But then you can also use it like a regular struct or object in Julia, where you can access the fields with this dot notation here. And so it's a very nice construct that, again, allows us to basically group together a bunch of values, but with the names assigned to each value. And this here is exactly what the output type of init params is. So we have these init params returns a name tuple of the parameter name and then the value associated with it. And it's a fixed length construct or struct because it's a tuple. Good, so that's the output here, but obviously you can easily define your own. So if you really want, you can define a different sort of initial parameters here. And when you define your own name tuple, in general, we recommend putting a semicolon at the beginning because if you don't and you have a single name, then this will not be correctly defined by Julia as a name tuple. This will be interpreted as just parentheses around the expression a equals 1 instead of a name tuple. And so we always recommend putting this at the beginning because then you can define even a single element name tuple. But in general, if you want to define your own initial conditions or not initial conditions, but initial parameters, then you can also do it here. So you can just write your own popcl value and define it however you want, and then keep doing that for all of the parameters. There's also a lot of different ways to sort of programmatically, let's say you define init params here, but you want to replace one value, then there are some nice tricks to do that. I suggest you check the name tuple documentation, and I think there's a package called name tuple tools, if I remember correctly, that also allows you to do a lot of smart and nice manipulation of name tuples using just single lines of codes usually. So yeah. But this is not really the focus of today, but let's say for now, we're just going to use this output of init params from the model, which we have already defined or hard-coded directly into the model. Now, the fourth argument is going to be the fitting algorithm or the estimation algorithm. And this can either be things like Laplace or FOCE. And FOCE in Pumas is with interactions by default. So if you come from non-mem, there might be with and without interaction. In Pumas, we always use with interaction for FOCE, for even FO, and for Laplace. So it's always with interactions. And in general, this pattern here is actually going to be repeating a lot. So the fact that we try to always use these sort of patterns here, where we start with the model and then have the data and then some parameters, population parameters, and then the fourth argument can change from one function to the other. But for example, the simulation function is called simobs. It takes same exact arguments. And so we try to be as consistent as possible with the orders, for example, to make sure that, or with the order of these parameters or these arguments to the function, so that it becomes easy to remember. So it's always the model, the data, the parameters, and then the fourth argument depends on the function that you're passing these arguments to. So in this case, it's a fit function, and so the fourth argument will be the algorithm that you're going to use for estimation. Now, I'm going to go ahead and run this. It does take a little bit of time, but while it's running, I'm going to walk through the outputs and explain what's actually happening there. So the first thing is there will be no output, and that's because it's compiling. And I did say that it takes a bit of time to compile. And every time you redefine your model or you define a different model, it will need to recompile. And so it might take a few moments initially for compilation. And then once it's started compiling, it will tell you something like this, where, or once it starts running, it will tell you that it's checking the initial parameter values. Now, the way Julia works is as it's going through functions, sometimes it compiles, it needs to pause again for some compilation to happen again. And so here it's not, what it's doing here is it's computing the log likelihood or the marginal likelihood using FLCE as an approximation, and then computing the gradient to make sure that both of these are finite at the initial parameter values. And so one thing that any optimization algorithm needs is usually that at the initial points, you need to have finite objective. So whatever you're trying to minimize or maximize needs to be finite, needs to be a number, and then the gradient also needs to be finite. And so that way you can start your optimization essentially. And so here it's, even though it's taking some time, it's not actually doing all this time just to check, but it's still compiling the log likelihood function, compiling the gradient function, etc. And when models tend to be big, they can take a little bit of time to compile. And so that's why it's taking some time here. And I suspect the fact that I'm running on my own laptop and having Teams call is not helping. So you might see it a bit slower than usual. But let's give it a few moments and then see what comes up next. Okay, so that was good timing. So the initial, here it says the initial negative log likelihood and the gradient are finite, check passed. So now we can go ahead with the optimization, and you see that it's actually been a lot quicker since. So this is the iteration number of the optimization. This iteration number indicates that it's calculated the objective, calculated the gradient, and then did like a line search that needs to calculate the objective multiple times. And so it's doing all of this in very quick times, right? It's not taking that long. And that's because it's already finished compiling. So you'll see it's a lot faster now that it's finished compiling. So maybe one thing that's worth mentioning is that the fit function itself has a lot of options, and many of these options should be documented in the Pumas documentation. So please take a look at that, and it will tell you what the main options are for this function. For example, you can set things like the differential equation options if you want to modify that, and things like the optimization tolerances and so on. But let's take a look at this trace here. So this is a trace that we'll be printing whenever we are doing this optimization. And in this trace, we have the iteration number here. We have the function value, which is actually the negative log likelihood. So this is the objective function value of Pumas, which is actually the negative log likelihood directly, unlike in non-mem, for example, which is -2 times the log likelihood plus some constant. And so, or rather minus some constant. But in Pumas, it's actually the negative log likelihood, which means we should try to minimize it. So this should be minimized as we're doing the optimization. And then this here is the gradient norm, or the norm of the gradient of the objective function value. And so obviously, as the optimization proceeds, we expect that the gradient norm should come closer and closer to 0. And so we'll see here that it was e plus 6, and it then became e plus 5, and so the number is decreasing. And also the gradient norm is slowly decreasing as you proceed through the optimization. And eventually we expect these numbers to be small enough. But this model takes I believe it took about 3 minutes or so, maybe 4 minutes to finish running when I tried it before. And it's finished now, so that's good. And so what you see here is that the gradient norm is smaller than before, but it's actually not too small. So it's still 0.899. And the objective function value is shown here. It's just 992.44. And that's, again, the negative log likelihood. And so sometimes when you're running these fits, when your data set is sufficiently complicated, or your model is sufficiently complicated, sometimes your optimization will terminate because it's not able to improve the objective function value further. Not necessarily because it truly converged to like a stationary point. So a stationary point is a point whose gradient norm is 0. So a gradient norm is very close to 0. And so sometimes you'll see that it might converge, or it says that it converged, and successful minimization, but you look at the gradient norm and it's still not quite 0 yet. Now it's compared to 10 to the power of 5, which we started with. So if you remember, we started with a gradient norm of 10 to the power 6. This is 7 orders of magnitude less. So you could be happy enough with that. In my case, sometimes I like to push it a little bit further. And I do this by resetting something called the inverse Hessian approximation in the optimization algorithm that we use. So I just restart the fit, essentially. But I restart the fit from the final parameter values. So if I call this coef function, coef is another function that we provide from Pumas. If you call it on the output of fit, you get all of the fitted parameter values at the end as another name tool. So this is just like the init params output, but these are the fitted parameter values. And so what I do here is I call the fit function again, but in this case, I initialize it from the previous output of fit. And I also initialize the random effects from the empirical Bayes estimates coming from the previous fit. So this makes sure we're really continuing the fit from before, but the only difference is that now it's going to restart the optimization, which means that it will restart the inverse Hessian approximation of BFGS. And if you got stuck in the line search here, you might you're less likely to get stuck, or slightly less likely to get stuck when you do this. And so when I did this, it actually continued optimization, or continued improving it a little bit more, not significantly. And you'll see there were some numerical errors because the optimization inverse Hessian was now reset, which leads the line search to be the line search can explore some parameter values that give you numerical errors in your model, but you also see that the gradient norm is a lot better now, right? So we're able to push the gradient norm further down, and it was able to optimize it a little bit more. I think the log likelihood just, or the negative log likelihood just decreased by 2 more points. It wasn't that much, but still, this looks a lot better than 0.9, right? This is 10 to the power minus 3 now. So hopefully this is a nice trick that you can, by the way, use in non-mem as well. The same trick. Try to initialize the fit. I don't know if it's easy to initialize the random effects in non-mem. It might not be that easy, but you can do some similar tricks, I believe, in other software as well. Good. So with that, we have our own fitted model, and so this FPM here is a fitted Pumas, right? And that's what it stands for. And you'll see this FPM everywhere in our documentation and tutorial. It usually stands for fitted Pumas model, but it's just a variable name. You can call it whatever you want. And so this here is the output of fit. Now, once you called fit, there are a couple of things you can call on the output. And so if actually let's do type of FPM. So type of it again is this function that tells me the type of this thing. And you'll see again, it's a very long type, but the first part is the most important part, which is that it's a fitted Pumas model, and the type lives in the Pumas module, or comes from the Pumas package, right? And you can actually call a whole bunch of things on FPM. Like we have a bunch of utility functions that allow you to extract different information from this fitted Pumas model. And so I can extract the coefficients, for example. I can extract the coefficients here using the coef function will give me a name tuple, which I can use to maybe pass it to a simulation function or to another fit function, right? So this is useful when I want to continue programming. But there's also another function called coef table, which is more useful for presenting the results. If I want to maybe present the results in a report or something, then the coef table might be a slightly better form to present it in. And so this actually gives me a data frame. So for example, I can take this then data frame and print it to a CSV file and then send it to somebody else, right? So if I'm interested in summarizing or in showing the results, then you can use coef table, or alternatively, you can also use this coefficients table, which also has things like the description of the parameter. So it will be the parameter name, the description of the parameter from your model, and then the estimate, right? Again, this will be a data frame, so you can save this to a CSV file and send it to your colleagues to take a look at it. And so that's when you're interested in displaying things. But if you're just interested in getting a name tuple out to then pass it to a simulation or to do something else with it, then you call the coef function on FPM. Then we have this icoef function, which stands for individual coefficients. And what it does is it basically returns the output of the pre-block for every individual and for every time point. And so this pre-block here, I mentioned that this yesterday, this is essentially a function of time, because the pre-block can use the t variable here to have any explicit dependence on time. For example, if you're writing a disease progression model and you have an explicit dependence on time, then you can take advantage of T in this pre-block. But this will also be different for every subject because every subject will have a different value for the covariates and even different values for their empirical Bayes estimates of the random effects. And so the output of the pre-block is different for every subject, but it could also be potentially a function of time. And so the ICOF function allows us to get this output of the pre-block. So let's take a look at what it looks like. And so if you call ICOF on FPM, you get some vector. And so if you look here, you'll see that it's a vector of something. And this something is what we call a interpolation struct array. It's not too important. It works like a function. But the way you can get, for example, the ICOF of the first subject at time 0 is, let's say the ith subject at time t is using this notation here. So first you can get the ith subject. So let's say I equals 1. And so let's get the first subject's ICOF. And then I can call this like a function with time equals 0. And it gives me the individual parameters together with the ID, just for further identification of these parameters. So is there any question? Okay. And so we have this name tuple now, essentially, that has all of the variables that were defined in the pre-block, including time itself, which I defined a variable called time, and I made it equal to t. So this is the time point at which the value is computed, and this is the ID for which the subject, or the ID of the subject for which these values were computed. And these are all the variables defined in the pre-block. You can get them through ICOF. And for the random effects, it will be using the empirical Bayes estimates for each subject. So that's how these values get generated. Speaking of the empirical Bayes estimates, you can also get them explicitly using this empirical Bayes function. So empirical Bayes function will again return a vector. This time it's a vector of name tuples. And one element once again for each subject. So if I want to get the empirical Bayes estimates of subject 1, then I can use the indexing notation because it's just a vector, and it gives me a name tuple of the empirical Bayes estimates of that particular subject. And I can then go ahead and use this for simulation or use it for maybe trying different doses and so on for this subject and seeing how they respond, or predicting the future and comparing the future predictions to the observations. So we'll see some examples of these things in the next few sections. And so this is how you compute the empirical Bayes estimates. If I want the log likelihood of the model, I can call the log likelihood function, which gives me the log likelihood value. Now recall the objective function value is actually the negative log likelihood. And so you'll see here that the final value is 992. Here the log likelihood is minus of that because this is the negative log likelihood being minimized. And here we also display the log likelihood value in the log here, or in the printed description of the fitted Pumas model at the end of the fit. So the log likelihood function can be used to get the log likelihood of the fitted Pumas model. Now the log likelihood function itself has another call it, so you can call it directly with, again, the same arguments that I said. So we said model, data, coefficients, and then algorithm. You can use those same arguments, model, population, and then the parameters, which is coming from the coef of the fitted Pumas model, and then the algorithm. And this should also give you the log likelihood. This should give you the log likelihood, if I spell it correctly. But you will notice something here, which is that the value of the log likelihood we get here is actually very different from the value of the log likelihood we got here. And this is something you may also notice if you do this in non-MEM. And that's because when you call the log likelihood like this, it actually does not initialize the random effects from the empirical Bayes estimates. It initializes them from 0. And the choice of the empirical Bayes estimates can have a significant impact on the value of the log likelihood when you're using the FOCE or Laplace. How you initialize the empirical Bayes estimates can significantly impact the log likelihood value. Whereas if I call log likelihood on the fitted Pumas model, it actually initializes it from or initializes the random effects from the empirical Bayes estimates. And those typically, during the fit, for example, we typically going from one iteration to the next. We always initialize the random effects from the empirical Bayes estimates from the previous iteration. And so the path that it takes or the log likelihood estimates that you get from the end of a fit might be very different from the log likelihood that you get if you reinitialize or reset your random effects to 0. And that's generally a problem. And so you would need to, like there are different ways to try to address this, either just call log likelihood directly on the FPM to make sure that you use the same random effects. The other thing is that in the future, I don't think it's supported. We also plan to give the option to define the initial random effects here. So I can also initialize the random effects from the empirical Bayes estimate. And so, but this is not supported yet. So this is hopefully something that we are interested in supporting in the future. But this is something to keep in mind when you are computing log likelihoods, even in other software. The other option is that you can try changing the internal optimization algorithm. And so sometimes when you change the inner optimization algorithm, you also get a better initial, or even if you initialize the empirical Bayes estimates from 0, you might have slightly better estimates of the empirical Bayes estimates at the end. And that could also fix this problem. I don't know if this is going to work, but let's give it a shot. And BFGS is actually defined in a package called Optim. So let's see if I can. I'm improvising a little bit, so hopefully it doesn't come and bite me afterwards. But you'll see that changing the algorithm here also did not seem to help that much. So it is quite persistent, and because the model here has quite a few random effects as well. So if you look at this model, we have I believe 3 random effects for PK, if I remember correctly, and 4 for PD, and we have 1 more for lag. So we have 8 random effects in this model. And so models like this, which tend to be over-parametrized in terms of the number of random effects, can also have multiple local minima in the random effect space. And so for a specific set of values for the population parameters, when you try to get the empirical Bayes estimates, you could have multiple different local optima. And that means that it's the output that you get is sensitive to the initialization or the initial value of the EBEs or the empirical Bayes estimates. And that can also affect the log likelihood approximation. So again, that's an unfortunate side effect of these methods, FOCE, for example, in the class, that they tend to be sensitive to how you initialize the random effects in the inner optimization. So something to keep in mind. So this is the log likelihood value. I digressed a little bit, but this is the log likelihood value from the fitted Pumas model. And then you can use that to also calculate or use the same fitted Pumas model to calculate the AIC and BIC, the information criteria that are typically used for model comparison. And then let's say I would like to know the most influential subjects. And so what does that mean? It means that maybe some subjects might be very well fitted and some subjects might not be very well fitted. And so find influential will basically compute the individual log likelihoods, or rather the negative log likelihoods of the individual, and sort these individuals based on their negative log likelihoods. And so that should give you an idea, because when the negative log likelihood is high, that usually is a sign that we did not fit the subject very well, or that this subject might be a potential outlier. It's not guaranteed, but it seems to be that this subject number 15, for example, was fitted slightly worse than everybody else. Everybody else had their negative log likelihood around the same value, ranging from 55 to 23, but it seems to have one subject. We seem to have one subject that was not fitted very well. So this can be used to query your or understand which subjects were not fitted as well as the other subjects. And so if I look at the data frame, so I'm using this R subset without the bang to make sure we don't modify the data frame in place. I just want to sort of get a subset of this data frame for ID equals 15. So this is the same syntax we saw yesterday, just to take a look at this particular subject. And, not sure if there's anything obviously weird with this subject, but maybe the fact that, I don't know for a fact what's different about this subject, but that would be a candidate subject to look at and see if anything funny is going on there. Now, we saw that a fit can take a few minutes, sometimes much longer as well. And so sometimes you don't want to rerun this fit over and over again every time you have to do this analysis. And so what we do to avoid that is something called serialization, which is basically a fancy name for saving. And so you want to save your fitted Pumas model to a file. Now, the file format that we typically use for a serialized Julia code or Julia structs is this JLS file format. And it's kind of, you can kind of change it if you want to, but that's the recommended file format to use for these binary files that are basically saved Pumas models or Pumas fitted models or any kind of Julia object really that you can serialize. And so the way to serialize an object is to call using serialization, which is a module or a package in the standard library in Julia. And so this you always have access to it. And then you can define the file name, and then you can call the serialize function, with the first argument being the file name and the second argument being any object that you want to serialize. So here I can serialize like a name tuple if I want to. I can serialize anything, right? It's any Julia object. And so the fitted Pumas model is the object that we would like to serialize in this case. So let me go ahead and call this function. And then if you look at the output, I should be able to see, or you should be able to see the JLS file here in the output at the end. And now if you want to load this file, you can call the deserialize function. So let's say you've went and taken a break, you disconnected your Pumas or Julia Hub, and then you came back here. You don't need to rerun your fit. So you can just put this line here, deserialize instead of the fit, right? So typically, for example, what I do is I define an if statement and I see if a file exists. So I can check if a file exists, and if it does, then I can call fpm equal deserialize of that file. And then if it doesn't exist, then I can rerun the fit essentially. And that way, if I want to sort of reset this, all I have to do is just delete the file here, and it will automatically rerun this. Or if I move it to another, if I move to another folder where this file is not available in the current folder, like I can move to a new folder here, and then this time it will rerun instead of loading. So I can change to this directory, and then if I call isFile will not be true. But right now, isFile should be true because I just serialized this, and so there is a file in the current directory called warfarin_fpm.jls, which is the value of this file name here. And so this is how you can do things like caching. We have other ways to do caching as well using a package called Quarto tools, especially if you're doing it from within Quarto. So we have support for Quarto or for Julia and Pumas code within a Quarto document, if you prefer that. And so there are other packages that give you conveniences that you can also use, I think, inside or outside of Quarto as well. So Quarto tools is a nice package that you might also be interested in, but I'm not going to cover it in too much details today. Good, so that's how you save a model. And I mentioned how you can also compute the log likelihoods. And so let's see how we can compare this to non-mem. So one usual exercise for people when translating models in general, it's recommended to always compare the log likelihood values at the end, even at the beginning. So when you're computing the initial log likelihood, like a non-mem, you will do max val equals 0. You can do the same thing with the log likelihood function in Pumas and then compare the values. The problem is that in non-mem, it doesn't actually report the log likelihood directly. It reports two quantities. One is called objective function value with constant and without constant. And the way to map between the log likelihood and these objective function values to know whether or not you found a comparable fit with a similar or better log likelihood value is that you would need to get the log likelihood from Pumas, and then minus 2 times the log likelihood will be the non-mem objective function value with constants. And then if you want without constants, you need to subtract the number of observations times log 2 pi. So this is the constant that non-mem will automatically remove when optimizing or fitting a model. And so the default objective function value, I believe, is the one without constants. But at the end, non-mem also reports this just for ease. Notably also, this number of observations is only the number of Gaussian observations. If you have some non-Gaussian observations in non-mem or in Pumas, like censored or something like that, then this number of observations will technically not be correct. So you would need to remove any sort of LLOQ values and so on from there. And so it's always maybe easier to use the width constant, because then you can directly get -2 times log likelihood from Pumas and compare it to objective function value with constant, and let non-mem figure out how to add the constant depending on which constant exactly it's used. For different models, it probably uses a slightly different constant. So it's probably best to stick to this, especially if you have censored or using M1, M2, M3, and 4, etc. Then it might be easier to use this comparison here. Good. So let's see how we're doing on time. So we're still discussing model diagnostics, metrics, and plots, and we went a little bit over time, but we still have quite a bit of time. So let's keep going. Okay, so let's move on. So the next thing you probably want to do, besides checking the log likelihood, is to take a look at maybe individual predictions versus observations, and then visual predictive checks. So let's start with the visual predictive checks. So the easiest way to call or to get the VPC is to call this VPC function, which stands for visual predictive check. And you can call it directly on the output of the fit function, which is the fitted Pumas model here, and then you can specify which exact variable you want to see the VPC of. And so in this case, we had two responses, concentration and PCA. And so I can tell I would like the VPC, or the visual predictive check, of this concentration. And this does not actually do the check, it just computes all the values needed to do the plot. So it doesn't actually do the plot for you. But to do the plot, you need to call another function here and pass to it all the plotting options that you need. And so this only does the computation needed to do the plot, but then this will be doing the plot with all of the different options that you might be interested in. And so the VPC plot function will take the output of the VPC function as its only argument, and then it will take a bunch of options here as keyword arguments. And so let's take a look at what this plot looks like. So if you look at the VPC, it looks something like this. And then I'm going to add a legend. So this is how you can add some additional legend and then display it under the figure here. Good. And so this one looks like it's okay. So maybe to recap, you probably already know what a visual predictive check is and what it does. But basically, the black lines are all the observation quantiles. So in Pumas, we use quantile regression rather than binning. And so we try to figure out what the quantile line is for the observations. And then we do the same thing for the simulation. And so we simulate multiple synthetic population. Actually, the exact procedure is described in this slide deck. If you go towards the continuous visual predictive check, I have the exact procedure that we use to do the VPC. So first, we will simulate a synthetic population. So when you call the VPC function, it simulates a synthetic population given a number of samples. So it will simulate, for example, 500 or 499 for some reason, synthetic populations. Each synthetic population has the same size as the original population that you have, or the data that you have. And so if I have 30 subjects in my data, then I'm going to get, let's say, 499 different populations. Each of them has 30 subjects. And those populations, when you're simulating values for the random effects, and you're simulating values for the error model at the end, or the observation at the end. So we're sampling from two different places. You can customize all of this stuff with different ways. Like you can only sample the response instead of the random effects if you want, but usually it makes the most sense to just sample values for the random effects as well as sampling values for these observations here. And that's how we get the synthetic populations. And then we do this over and over again 499 times. By default, you can customize this with the number of samples. And then once you do this, what we do is we do stratification. So sometimes you'd like to see a stratified VPC. And so if you pass a certain stratification option here, if you pass a certain, I think it's called stratify by, if I remember correctly. And if I pass what I want to stratify by here, and if you forget the options at any time, remember you have the help mode that you can go to. And so if you go to the Julia REPL and then write the question mark, you get to the help mode, and then you can write VPC and you'll see the documentation there. of that VPC, and you'll see that there is a stratify by option that allows you to pass a vector of symbols. And so I can pass things like stratify by, and then here could be sex, for example, or whatever covariates that I have in my model, and then that can give me the stratified VPC. Okay. Now, anything that you need to pass to change the computation, so the computation of the quantiles will change if you stratify it, because now you need the stratified quantiles, so that should go into the VPC function. But any just visual options that are just for the plot will be going into the VPC plot option. And again, you can check the documentation to see how to customize these things. Good. So let's go back here. So we're doing stratification of the observed variables or the observations and also the simulated population. So we have the single population that was observed, and then we have the 499 populations that were simulated, and we do stratification for each of those populations. And then for each simulated population stratum, or for each, like let's say we're stratifying by sex, then for let's say male and female, then we do a smooth quantile regression. And so we're not doing binning for each stratum, we're doing quantile regression. And the number of nodes used in the quantile regression is picked from the data directly. And so if you're familiar with quantile regression, you need to specify the nodes, but you also need to specify the bandwidth that does smoothing. So it does something called smooth quantile regression. And so the smoothing comes from this bandwidth, which by default is actually set to a pretty maybe useless value, which is 2. And typically you want to adjust the smoothing effects, which is useful for plotting. So if you look at the VPC and it looks too raggedy in your VPC, then you probably want to adjust the bandwidth of your smoothing to get slightly more smooth curves. But in this case, it looks okay enough. So we didn't need to do that. But the smooth quantile regression takes in this number of nodes, which defaults to 11, and takes in the bandwidth. And by default, the quantiles we're interested in getting from the quantile regression is the 0.1 quantile, 0.5 quantile, which is the median, and then 0.9 quantile as well. And so these are the default quantiles, but you can also customize with the quantiles argument here. So we have this quantiles option, which you can customize to any other quantiles that you're interested in. And then once we do that, so remember we're doing this for every simulated population. And so we have 499 curves, essentially 499 percentiles for the 0.1 percentile or quantile. We have 499 curves or functions of time for the 0.5 and 499 functions of time for the 0.9 percentile. And so we have all these different percentiles. And now what we do is we find what I call here the hyperquantiles. Some people would call this the confidence interval for the quantiles, but it's just a summary statistic rather than a confidence interval. And it's just taken the quantile of the quantiles because we have these 499 values. And so now it's trying to take the hyperquantiles, essentially, or the quantiles of the quantiles. And we do this by taking the, again, just the percentiles, the empirical percentiles or quantiles from these values. And then that's exactly what becomes the bands. And so the blue band is essentially the quantiles of the simulated 90th percentile. And then the gray band represents the quantiles of the simulated median. And then the other blue band is the quantiles of the simulated lower percentile or lower quantile, right? And the hope here is that, and the medians are also plotted with the blue lines here. So when you write here sim quantile medians equal true, it will also plot the median of each quantile and not just sort of the range or the bounds of the quantiles. So if that's too confusing, maybe try to read through this slowly and you will be able to get it. And then we also do the same thing for the observed population or for the data itself. And that's how we get these functions. So we only have a single observed population. So we only have a single function of time for the quantiles, for the 90th percentile, the median, and the lower percentile. And that's the black line, right? So the black line is the only percentile curve for the single observed population that we have. And the hope here is that basically the goal of the VPC is to compare the distribution of the simulation to the distribution of the data that we have. And so if the distributions are comparable, you would expect that perhaps the median line would be close to the observed quantiles. So the median of all these quantiles here, of the simulated quantiles, will be close to the observed quantiles. So the 90th will be close to the 90th, the median will be close to the median, or the 50th to the 50th, and the 10th percentile observed quantile will be close also to the simulated 10th percentile. And so that's the hope. And the hope is also that the bands here, which again some people call confidence interval, the hope is that this will encompass or include the black line. And whenever the black line deviates or moves out of this band, you will see some red signs here. So maybe you see a little bit of red at the beginning here, and this indicates that there's potential outlying behavior. And this could be attributed to model misspecification or to maybe some data being odd. So maybe there's one part of your model that seems to mismatch the data for some reason, but usually this is an indication of model misspecification. It could be that your error model is misspecified or your random effects distribution is misspecified, and that's why your simulations are not matching your observations. But this looks like a generally good VPC. The distributions seem to match pretty well, and the quantile curves are all pretty close to each other. And so this one is a good looking VPC. Now I can call VPC on the PD variable and take a look at it as well. And it's doing the exact same thing, but now for the other response. And you'll see that here it's almost exiting the interval a little bit. And so maybe this part of the model can be improved a little bit, but overall it looks like it's a good model. And the distributions seem to match pretty well, being the distributions of the population that was observed, the distribution of the simulated data that we simulated. Okay, so we have now showed how to do this visual predictive check. So the next step, this is actually usually called straight out after a fit, is this inspect function. And so inspect function will take a look at the fitted Pumas model and then compute a whole bunch of different diagnostics that might be interesting. And then I can pass this then to different functions to extract these diagnostics afterwards. So here it's computing all these diagnostics and storing them inside this object here, which has the type. So let's take a look at the type of this. It's a very long type, but the most important thing is the first part, which is a fitted Pumas model inspection object. And this just stores a whole bunch of things like individual predictions, residuals, etc., which we can again query and plot and so on. Now, by default, it's going to compute something called the weighted residuals. And if you're not familiar with the weighted residuals, we actually explain them here in this section. So this is how to calculate or what are the weighted residuals and how they're calculated. But by default, it will compute the weighted residuals. But if you have non-Gaussian data, or if you have non-Gaussian data or even some non-Gaussian random effects, this might not work. And so you might need to calculate something called the NPDEs, which relies on simulations essentially to calculate the residuals and the distribution of the residuals. And so you can also pass this additional argument, I believe it's called NSIM. And when you do that, it will calculate NPDEs and expected weighted residuals from the simulations directly. And this works for any kind of data or any kind of distribution. And so if you're using maybe a censored error model or something like a categorical or discrete error model or like a distribution for your data, then you probably want to pass this NSIM as well to get the simulated residuals and not the sort of FOCE version of the weighted residuals. Good. So let's call the inspect again without the NSIM for now. And let's then call this. So one thing you can do with the inspect object or the output of inspect is you can pass it to a data frame. And this will construct a data frame out of the information included in that inspect object, which will include things like your data. So you already have your time, your EVID. So if we take a look at we call the names function on this data frame, you will see that if we print the names function or the output of names, you will see that it has things like ID, time, EVID, so the things that were already in your population, things like duration and SS and II, which are useful when you have events For many of these things, it will probably just be the default value. It has the covariates that were defined in the model, including the ones that were derived from the data frame, for example, and read into the subject. Things like time after dose, the dose number, if you have multiple doses. And by the way, in the VPC, you can also make it with time after dose. So you can specify here the covariate, for example, and make that time after dose rather than nominal time, if you're interested in that, or any other covariate. So you can do a visual predictive check with respect to any other covariate being on the x-axis and not just time. But that's a digression. But the point is that here we have additional information like time after dose number, and then we also have the population predictions. This is the population prediction of the concentration, and then this is the individual prediction of the concentration. The difference is that the population prediction will be using essentially the median of the random effects. And so if you look at the random effects here, they're all Gaussian. So we're just going to be using 0 for the PK, for the random effects, the PK random effects, the lag, and the PD random effects are all going to be set to 0 when the predictions are made. Now, what's a prediction? The prediction is basically the mean value of this distribution. That's the prediction. And so the mean value of this distribution is just CP. The mean value of this distribution is the prediction for PCA, which is just turnover. Right, and so that's the conc underscore pred is the mean value of the distribution given the random effects being set to 0, or the median rather, to be more general. And then the IPRED is also the mean value of this distribution, but the random effects are now set to their empirical Bayes estimates for each subject. And so for each subject, we find the empirical Bayes estimates coming from the fitted Pumas model, which, as I mentioned, might be sensitive to how you initialize it. But in this case, it's using the same empirical Bayes estimates at the end of a fit to make these predictions, and then it makes the prediction for each subject now. Yeah. So usually the PREDs will only be different from one subject to another if they have different doses, for example, or different covariates, and the IPREDs will be different even if two subjects have the same dose and same covariates, because they might still have different random effects that were used to make these predictions. We also have prediction for the other variable, which is PCA pred, PCA IPRED, and then we also have all of the random effects stored here as well. So you will see that we use this subscript notation. The way you write subscript notation is, for example, I can write eta like this with backslash eta, and then backslash underscore 1 and tab, and that gives me this nice subscript notation. So it's a little bit fancy, but it's not that difficult to write. So again, backslash eta, and then backslash underscore, and then maybe 2, and then tab, and that gives me the next subscript. And so if you want to access the specific subscripts or like the specific variable, you can write it like this. So pk underscore eta, and then maybe 3, right? And that is exactly this this name over here. Okay. And so we are using these subscripts to indicate that this is the first PK eta, or sorry, this is the first PK eta, second one, third one. We have the lag eta, we have the PD etas here as well, 1, 2, 3, and 4. And then we have the weighted residuals that I mentioned earlier that are computed for the concentration. So there's the population weighted residual, and then there's the individualized weighted residuals for the concentration, and then for PCA, and yeah, for PCA as well. And WRes approx, I believe that's just the algorithm that was used. Let me double check. Yep, that's FOCE is used for the WRes approximation. And then we also have the output of the pre-block. So all of the values that were defined in the pre-block are also going to be here. And these will be defined for every time point that's in your data set, that was in your original data set. And so we compute these values again here. And then we also have additionally the values of the output of dynamics, so depot compartment, central compartment turnover. If you want to inspect these values at specific time points, you also have access to them here, including the lag, for example, as well. So this is those control parameters that were defined. All right, so you basically have access to almost everything you need to inspect after you've fitted the model, and that's why this function here is naturally called inspect. Okay. So you can call the inspect function, computes all these quantities, and then you can call the data frame function on that, and it summarizes it in a table for you, which again you can write to a CSV file and post-process it later, for example. So if you're running this fit and it takes a long time, just make sure you save this at the end, and then you can take a look at it at the end after the fit is finished. Good. Now, what I'm going to do here is I'm going to just change so I want to plot some things. And so I'm going to define a new variable that just changes the sex field from 0, 1 to female and male. And I'm defining, so I'm using this R transform, or rather just transform macro here. And it's doing it in place. So it's defining a new row that's this sex categorical or sex C, and it changes the binary or the 0, 1 encoding to a string encoding. Any questions? Okay. And now, let's say I would like to do some plots. I want to compare the individual predictions to the actual observations. And the way we are going to do this is using this package called Algebra of Graphics, which is a very flexible plotting package. It's open source in Julia and currently maintained by one of my colleagues at Pumas AI, but it is an open source package. And we have a lot of tutorials. We have some tutorials here on this package. And so if you take a look at this link, you will see that for a plotting package. It's not the prettiest homepage for the tutorials, but if you click on these tutorials, it shows you how to use these different like the different features of this package and how to bring a data frame in and then decide which x-axis you want, which y-axis, if you want to color by something, and then draw, and then if you want a scatter line or a scatter plot or a line plot, etc. So many different types of plots. And so we have all these different tutorials that might be useful to go through if you want to learn more about this, and then how to go or migrate from ggplot essentially to this algebra graphics if you're more familiar with ggplot. Okay. And there's also another package called Mackie, the jail, and this is what sort of algebra graphics is built upon or on top of. So this link is actually the algebra graphics documentation. So the first one was a tutorials, set of tutorials. The second one is the documentation that's part of this Mackie organization, but it's the algebra graphics documentation. And again, it has more details here on the specific syntax and yeah, just how to use the package in general. But in this case, what we're interested in is in plotting the individual predictions versus observations. And so we're going to use this specific sequence. And so the way algebra graphics works is you define the data first and you pass in the data frame, and then you use this algebra or algebraic symbols to essentially define how, like, to modify the plots step by step, and then maybe to add plots on top of each other as well. So if you want to add plots on top of each other, use plus. And I think if you want to just modify certain things or build a pipeline for a plot, then you use the multiplication. And so what we're doing here is defining the data first, and then we're defining the options for the plot or the main components of the plot, which is going to be, we would like the x-axis to have to be this particular field or column. So remember, this was one of the columns. The individual predictions of the concentration was one of the columns in this data frame that came out of inspect. Before that, though, I just drop all the missing rows. So any rows that have a missing value for concentration, I call drop missing. Again, notice there's no band here, so this is not in place. This is defining a new data frame now that has the values here. The rows where the concentration is missing are dropped, but the original data frame is still the same. It hasn't been modified. And so on the x-axis, I would like to use this particular column, and then I would like to rename it to this name here. This is what we saw yesterday called a pair. So this is like, you can just pass a bunch of pairs inside of this mapping function, and that's how you use the function. And so you define which x-axis variable you want to use, which y-axis variable you want to use, and the label of that axis. And then you can sometimes make a layout. If you want to stratify it by sex, you can write layout equals sex. If you want to color it, you can write color, for example, right? And so there's different options. In this case, I want to do the layout by sex. And then next, I'm specifying the type of plot. So it's going to be both a linear plot or a line plot plus a scatter plot. So I have this in a parenthesis. And so that means I want two different plots here. I want first a linear or a line plot, and then also a scatter plot on top of that. And then once I have my pipeline finished here or defined here, I can pass it to the draw function. So this is the same thing as just calling draw on all of this here, right? It's the same thing as just calling draw on the on this whole thing, right? That's just the pipe notation for that. So let's go back to this notation because it's nice. And so let's maybe first drop missing or call drop missing, and then define this or call this line of code. And so what we should see is a scatter plots stratified by sex with the encoding. We changed it to from 0, 1 to female and male. And then we have the x-axis is individual predictions because we defined it this way, and the y-axis is observation. And we have the line plot for each stratum for each sex, and then also the scatter plot of the points, right? And so overall, you see that there is a pretty good match between the individual predictions and the observation for this particular variable concentration. Now let's do the same thing for the PCA. Oops. I went ahead a bit, so we go back here. So now I'm calling both color and layout. So I'm also coloring by sex, and so you'll see that the two plots are now in different colors, just to showcase some more features, and you get the legend here for the color. And yeah, again, for the PD, it looks also somewhat reasonable. In general, what you hope to achieve is to basically have make this line the identity line. And so this line should be the y equals x line. And so you'll see that we have 40 on the x-axis, 40 on the y-axis, almost 60 and 60. And so if this line is close to the identity line, that's usually a pretty good indicator that the individual prediction that your model might not be biased, essentially. At least the predictions overall might not be very biased. Any questions? Okay. So good. So this is how you would plot the individual predictions. And so these are usually the most common diagnostics: individual prediction versus observations, and visual predictive check, right? Individual prediction versus observation will confirm that your model is able to predict for each subject. And so it would basically confirm, usually we use it to confirm that the model is correctly defined. The structure of the model is itself sufficiently flexible and correctly defined, such that I can, maybe not correct is a strong word, but at least sufficiently flexible and is able to fit the data, and it's not very biased. We also have a bunch of other plots that I'm going to show you that can help us evaluate this. But this is a very key plot, and if you see that there's a big mismatch, then it probably means you need to go back and change your model somehow. Maybe your covariate model is not good, maybe your dynamics is not good, right? Maybe your error model here is not good. So some part of this model needs to change. And the visual predictive check, it makes sure that your random effects distribution is also well defined. Because if your random effects distribution is extremely wide, like if you have too much variability here, and if the distribution here is not matching your data somehow, then the distribution, the VPC will also not match your data, and you might have too much uncertainty in the simulation compared to the observed quantiles. And so obviously, the VPC is also affected by the rest of your model, but this is maybe the individual prediction versus observation can also give you a more direct look at whether or not your model is able to even fit the data to begin with or not. Good. So let's take a look at a few other diagnostic plots that are usually interesting. So there's observations versus time, which just shows you the overall trend of your data. And so this shows the raw data. The black points are all the raw data. And then there's a low S, basically a curve that we just fit through it. So this is not from the model at all. This is just basically a line that was fit through all these points. And so that just helps you show the trend of the data in general. And then there, you can do it for an individual subject. And so I can get a specific subject here and show the raw data for this subject. And so I believe there was the subject 14 had ID 15. So let's take a look at subject 14. And this was a subject that was somewhat behaving oddly, or had an extra, like a higher negative log likelihood value than the rest of the subjects. And so, yeah, I'm not sure if anything here might be visible just from the plot, but maybe they just, this subject had an extra low curve for the PCA. So the PCA goes down to, let's say, about 15. Whereas in the population, most of the values are maybe around 20 to 25. And so maybe that's because that subject seems to have a slightly lower than usual PCA curve. And that's why it wasn't fitted as well. And also it had this extra large negative log likelihood. Okay, And we see here the so you can also call the observations versus time directly on the population. So you probably want to call this before you even start the fit, just to take a look at your data. And so you can call it directly on the population as well, and not just on the inspect outputs. Okay, and then we have a function called subject fits, which lets you see the individual fits for each subject. So this is somewhat similar to the individual prediction versus observation, but it shows you over time as well. So it shows you two plots, one for, or rather sort of three plots, one is scatter plot of the observations of each subject. And in this case, I picked only the first 16 subjects to be able to fit it on a page. You can generally paginate these and create multiple pages of these plots. But here I'm just showing one of these plots. And so let's maybe just show 12 of these. Get a bit easier to read or to see. But you'll see the black points are all the data itself, the raw data. The red points are all of the population predictions, which use, again, the median of the random effects. And then the iPreds are all of the individual predictions, which use the empirical Bayes estimates of the random effects. And so we can do this for the concentration. We can also do this for the PCA. Again, let's take maybe, yeah, see all of them. And so top 14. Yeah. So again, this is that subject, right, that was behaving a bit oddly from everybody else. So you might also be able to tell something by looking at it here, that it seems to be under the trend somehow for the PCA, but maybe not. Anyways, so this is how you can show the subject fits to maybe take a look at the model, seeing if you're not able to fit. So in this case, it looks okay. But if you're not able to fit, where exactly are you not able to fit? If it's towards the end or towards the middle or towards the beginning, and then figure out or get some insights as to how to modify the model to try and fit this part of the data better. Okay. And we have the observation versus prediction plot. So this is the observation versus the so before I showed you how to do this with algebra graphics. In general, we recommend using algebra graphics and getting familiar and used to it because it's very powerful. You can customize it in different ways, but we also provide these out-of-the-box functions that allow you to take a quick look with just one line of code at these plots. Now, these plots, often people are unhappy with maybe some parts of it and they want to customize it. And then when you want to customize things, it's usually best to go back to algebra graphics and try to customize it here. And so we recommend using algebra graphics as much as possible for the final plot. But sometimes we're just looking at quick results. You want to use these one-liner plots to take a look at these quick results. And so this here will give you the observations versus predictions plot for each of the observed variables. And it shows you the lowest fit of the data. It shows you the identity line, which we expect to match with our sort of data or the like if you do a linear regression line of our data here, we expect to get y equals x at the end, roughly. And so this linear regression solution is shown in the green line, right, between all these points on the x and y axis. And then we can do the same thing for an individualized prediction. Obviously, with the population prediction, you get more variability here. The between subject variability is not sort of fully captured. And so the observation will be, the observed values will be a lot more dispersed, let's say, compared to the prediction. The same population prediction, you might have many different observations. But for individual predictions, because we're capturing the between subject variability through the empirical Bayes estimates, then you should see a lot less dispersion around this line. And so the uncertainty should always be smaller with the iPreds versus observation plots. Good. And then we can take a look at the weighted residuals over time. And this tells us if there is any sort of changes in the like the model misspecification, or the model might be misspecified in some parts differently from other parts, and the error or the residual that you get at the end, if it roughly matches, so we expect this to be roughly the standard normal distribution, and so we expect that for every time point we roughly have mean 0 and standard deviation of 1 with the weighted residuals. And so in this case, you see that the mean is close to 0 and the standard deviation, it seems to be also close to 1. And overall, it's not changing with time, which is something that we need to look for. And so if the residual distribution is changing with time, then this reveals that maybe your error model might be incorrect and you need to adjust for time somehow. That time was not correctly adjusted for, because it seems like your distribution of residuals changes with time. And so this can also be used to reveal any model misspecification that you may have. And so we have for the concentration, we have for PCA, the weighted residual distribution over time. And again, what we're hoping to see is a standard Gaussian. You'll see that maybe one area that we could try to look into is the initial condition of the PCA. The residual here seems to be quite far from the standard Gaussian, where the mean doesn't seem to be exactly at 0, and it seems to be a lot more skewed to the bottom. And so this is something that might be worth looking into to try and improve the initial condition of the PCA. Okay, and let's take a look at the next plot. And so the next plot is again weighted residuals versus prediction. And again, it's doing something very similar. We expect the weighted residual to be a standard Gaussian, and we expect it to not change with the prediction. So to be the same distribution with the prediction value. And so the prediction value is, in this case, going to be the concentration or the predicted concentration or the predicted PCA. And in general, if you have only a few data points or a few subjects, then these plots might have some noise in them. So you might not get very good looking plots, but you still expect more or less the distribution to be close to standard Gaussian for every sort of, if you take a cross section, a slice through the like x-axis for a value of 5 or a value of 10, you should be able to get roughly the same distribution. Again, another area that we could potentially look at is that when the population prediction is high, the residual seems to be incorrectly distributed, right, or somewhat misspecified here. And so this is an area where we could look at that the model doesn't seem to be doing very well for very high prediction values of PCA. That could be something that we can investigate further. Okay, and then we can do weighted residuals versus covariates. Again, we're looking for a similar thing, standard Gaussian distribution for different values of the covariates. Now, which covariate? We have all of the covariates listed here on the x-axis, and we have the residuals here for PCA and concentration. For each of those, this is the population weighted residual, and this is the individual weighted residual that we have. And in this case, you actually see that it's pretty good. Again, distribution is largely consistent across the x-axis, and it's more or less standard Gaussian, although it does maybe, again, at the initial value, it seems to be slightly less dispersed than the other values. And so that could be something to look into. Okay. And beside that, we can also look at the histogram of the weighted residuals. I did say that it needs to be close to a standard Gaussian, and so we can confirm that by looking at the histogram and seeing if indeed it is close or not. And it seems to be somewhat resembling a standard Gaussian, so that's good. Any questions? Okay, let's see how we're doing on time. So we've just finished the model diagnostics. So we are about 45 minutes late in the non-Gaussian random effects. We haven't started that yet. And so we have about 25 minutes more to go before we will take a 15-minute break. This break is non-negotiable. And so let's keep going with these and see how much we can finish over the next 25 minutes. Yeah. Any questions before I move on? So we've covered quite a bit of ground here on the API. We've covered all these different diagnostic plots, how to interpret them. We've covered the prediction plots and how to plot them, the algebra graphics and the different features that it has. We've covered inspect, the function, which is a very important function to look at the end. We've covered visual predictive checks, and we've also obviously covered how to compare non-mem and Pumas log likelihood values or objective function values, how to save fitted Pumas models, how to compare models with AIC and BIC, empirical Bayes estimates, individual coefficients, which is the output of the pre-block, and how to do estimation with different algorithms. Or rather, we just use FOCE here, but we could have also as easily used Laplace. What we didn't talk about is when to use Laplace versus when to use FOCE and when to use FO. And so in Pumas, we actually have FOCE support not just for Gaussian random effects and Gaussian data. And so even if you have non-Gaussian distributions here, for some of the distributions, like the beta distribution, for example, or the gamma distribution, or the log normal distribution, or even categorical, we have some generalized FOCE that my colleague and the boss, Andreas, he sort of generalized the approach that is commonly derived in non-mem, and he made it work for other kinds of distributions here. And so this is a very nice piece of work that I think might also be published soon, is my understanding. But the idea is that FOCE in Pumas works even for non-Gaussian responses, essentially. And so you can have here different kinds of distributions, and it might still support FOCE. Now, in some cases, you still cannot use FOCE, like at least not yet. We have some other works, like some other generalizations being worked on. But for example, if you have censored or truncated, you would have to use Laplace. FOCE would not be supported in this case. And so there are some distributions still that are not supported by FOCE. But with the random effects, and we will see the non-Gaussian random effects, you can use any non-Gaussian random effects here as well, again, including beta distribution, log normal distribution, gamma distribution, etc. And you have access to FO, FOCE, and Laplace. And whenever you have FOCE, you also have FO that comes along with it. So that's sort of the idea. And so in general, you should reach out for FOCE. It's generally fast. It's more numerically stable. You can actually prove certain numerical stability properties of FOCE, and you can showcase examples where Laplace would fail, but then FOCE works, and it's able to avoid some numerical pitfalls. And we also might have some work published about that at some point. But the FOCE is known to be more numerically stable, and so generally and faster, and so generally you should opt for that unless you can't because you're using censored, for example, in which case you would currently have to use Laplace. FO is maybe sometimes good for initial exploration, but it's generally considered inaccurate to the point where you shouldn't use it unless, again, your model is maybe way too slow with FOCE. And so FO could be used initially just to get some initial estimates or something like that, just for a few iterations, and then you can switch to FOCE. But FOCE is the recommended algorithm most of the time. Okay. So again, we've covered quite a bit. But if there are no questions, I'm going to move on with the non-Gaussian random effects and how to take advantage of them in Pumas. Good. Let's move on. So most of the distributions that we use here, actually almost, I think all of them, are defined in a package called distributions.jl. So distributions.jl is just a regular Julia package that defines many of these distributions. And so I can define, for example, a normal distribution, right? And if I don't pass any arguments, I mentioned that we use this idea of multiple dispatch in Julia, which depending on the inputs, it will do slightly different things. And so if I don't pass any inputs, it actually by default constructs a standard Gaussian with mean 0 and standard deviation 1. If I pass only one argument, I think it will use that argument as the mean. And then it will assume the standard deviation is 1. And if I pass in 2 arguments, then it will take the first argument as the mean, and the second argument is the standard deviation, right? And so that's for the normal distribution. Now, for the log normal distribution, it has very similar behavior, where with log normal distribution, the mean of the log scale, so the log normal distribution in math is basically when you have, so let's do a multi-line comment here. So if I have x is normally distributed, and then x of x, or the exponential of x, will be essentially log normally distributed, right? And so the log normal distribution is parametrized essentially by the underlying normal distribution, mean and standard deviation, right? So the mean and standard deviation values here of the log scale. So this here, for example, is y. And so the mean and standard deviation of log y, mean of log y, and standard deviation of log y are the parameters of the log normal distribution, right? And so it's parameterized by the normal distribution of the log of the variable. And so here I can again pass no arguments. And so the mean of the log of this variable will be 0, which means it will be centered around 1 because exponential of 0, the mean and the median will be 0. So the median of this will also be 1. And I can pass the mean or the median, let's say, in log scale here as well. And then the standard deviation of the log scale will be taken as 1 by default. And again, I can pass in the standard deviation in log scale, and it will be used here, right? And so this here is the mean and also the median of the underlying normal distribution. If I want to get the median of the log normal distribution, it's going to be the exponential of the median of the log of the underlying. So if the underlying distribution has a median of 2, then the median of log normal is exponential of 2. But the mean does not work like that. And so the mean of the underlying distribution is 2, but the mean of the log normal distribution is not 2 because the exponential function is not linear. So the mean doesn't work that way, but the median will. And so the median will always be the same. If you apply the same transformation, you get the median of the new distribution. But the main idea here is that you have access to all these different distributions, right? The beta, you can define the beta distributions with different shape parameters. I can define the gamma distributions, right? A gamma distribution here. And so we have access to all these different, the legit normal distribution, right? Even the multivariate normal distribution that we saw in the random block. So you saw this in the random block in some places. We have the multivariate normal distribution available outside as well. So again, all of these come from this package distributions of jail. And so I can define here a normal distribution with mean 0.0, so it's 2-dimensional. And then I can define, this is the identity matrix, that's a 2x2 identity matrix, or I can write it out like this. So I can write out the matrix notation like this. So remember, the way you construct the matrix, one way to do it is with spaces to separate columns and semicolon to separate rows. And so I can define a multivariate normal distribution like this, right? And if I remove the first argument, then it will automatically be set to 0, the mean, and this will be taken as the covariance matrix. And so this is why in Pumas, you always have the covariance matrix here for a multivariate normal, but for a normal distribution, the second argument is the standard deviation, right? And so because the distributions of JL, that's the convention that it uses, which is for a univariate normal distribution, the second argument is the standard deviation. But for the multivariate Gaussian, the second argument, or sometimes only argument, is the matrix, the covariance matrix. And again, it could be the second argument if you want to change the mean. So if I want to define the mean here as 1, for example, then that could also be done. So the first argument will be the mean vector, and the second argument will be the covariance matrix of the multivariate normal. Now, just like we have log normal, we have multivariate log normal as well, and it works the same way. And so it's parametrized by the underlying multivariate distribution. And so it's just a log of, it's the exponential of a normally distributed random variable. So whatever the random variable is, the underlying random variable, that's multivariate normal, we take the exponential of that, and that's how we get a multivariate log normal. And so the domain of this distribution, or the support of this distribution, is always going to be positive numbers. And that's something that you always need to think about when defining a distribution, is what's the support of the distribution. And so if I have a response variable, for example, y, that's only between 0 and 1, and so I know that my y is always going to be between 0 and 1, then I should not be giving it a normal distribution, because the normal distribution support is going to be from -infinity to +infinity. And so that's where things like the legit normal might be useful, things like the beta distribution might be useful, or alternatively, what people do is they apply the legit transform to y, and then they model the legit of y as a normal, because then the legit of y becomes normal. Right, and this is equivalent to using the legit normal distribution, right? So I can just directly call y equals legit normal, or not equal, but it's distributed according to the legit normal distribution. And so instead of transforming the data, you can just change your distribution to match the domain of the output, and that worked. And similarly, if you have only positive values here for y, then you should not be using normal, even though you might get away with it most of the time because your mean might be sufficiently far away from 0, your standard deviation might be small enough, and so the probability of getting anything less than 0 when you're simulating might be very small. But you still, to be more precise and correct and to match the domain or to match the support of your distribution, or rather of your data, it's usually best to maybe use truncated, for example, so truncated normal distribution here, and you can pass the lower bound of 0. So if you just pass this here, lower bound of 0 and maybe upper bound of nothing, so there's no upper bound, or you can give it a log normal distribution, right? Or you can give it a gamma distribution. So these are all distributions which support positive numbers only. So if you want to be more precise, if you're simulating, if you start maybe with a normal distribution and you're getting a lot of negative numbers, and you don't like that because it doesn't make sense to have negative concentrations, then you could use one of these additional distributions. So that's a good summary of maybe distributions in general. So let's move on and show how we can use these non-Gaussian or different distributions inside of our Pumas model. And so in the random block here, I can define, for example, instead of, so if you look at the previous model, what we do here is we define a multivariate normal distribution, and then immediately in the pre-block, we take the exponential of it. Now, the exponential of a multivariate normal is exactly a multivariate log normal distribution. And so instead of doing it this way in 2 steps, first defining a multivariate normal and then taking the exponential, we can just treat this directly as a multivariate log normal, or this whole thing can become now my pk eta. And so that's what I'm doing here. So if you go back to the model below, you'll see that I'm defining pk eta as directly the output of the exponential, and then I'm multiplying it here without taking the exponential, right? And so this allows me to build these compact models, like less verbose, easy to read, because I don't have these transformations baked into the model structure, but rather they're just baked into the distribution type. And so it makes the model a little bit more readable. And so I can also go further. So this is the first step. I'll show you different ways to also make the model even more compact. But yeah, so that's one way, right? And so what we did here was literally change every normal distribution to a log normal distribution. And then instead of taking the exponential, we just multiplied directly without taking the exponential, right? And that's probably the only change we did here. Now let's take a look at another version of this model where we can go ahead and even change the mean of the log of these random effects. And so instead of, so maybe let's take a look at the previous model. Here you see that we were multiplying the population parameter by the random effect. Instead of doing this, multiplying the population parameter by the random effect, what I can do instead is replace this by 1, and then go back here and essentially define or pass log of this parameter here. And so let's say I can do the same thing for all of the other parameters. And so if I set the mean of the log to log of popCL, then I don't need to have this anymore. This multiplication can be gone because now this variable will be correctly distributed and it will represent what we used to be the product. And so before we used to have a product, now we are directly reparametrizing the model such that this whole product is now pk underscore eta 1. And the way we can do that is by directly encoding this into the distribution. So using this directly here in the distribution. And so the log of this will be used here. And we can do the same thing for the other random effect as well, right? So log of this random effect and log of this here, or this population parameter, not random effect, right? And so if I take all of these logs and I put them as the mean of the log scale of pk underscore eta, then I can go ahead and remove this because now pk underscore eta represents what used to be the product, right? And so the model can now be made even shorter. Now, in the future versions of Pumas, we also expect you to, or we hope that we can actually use baseline covariates directly in the random block as well. And so I can go ahead and even do things like this, where I can define, I put the baseline covariate directly here, and then I can make this even shorter. And then once I'm at this point, now I can just like it's a lot simpler. Basically, you just there's the model is very easily readable, and I can take a look at this and see exactly what the mean is and what the standard deviation or the covariance matrix is. Now, maybe this is a bit subjective whether this is more or less readable, but at least to me, it seems like it's adding more and more structure in your model. Now, this is not yet supported, so we can't use covariance yet in the random block, but we hope to be able to in the next few versions. And this will actually unlock what non-mem usually calls mu referencing. And so this is sort of the Pumas version of mu referencing when you do it this way, when you put the population parameters directly in the random block here to define the mean of the distribution and even some baseline covariates, then that's sort of the Pumas equivalent of mu referencing in non-mem, if you're familiar with that. And the hope is that this will actually give you a pretty significant performance boost in some cases because it allows for more efficient computation of gradients. So not only does it make your model look cleaner, but it can actually make your model also run faster when fitting the model. So that's another added advantage of that. But again, for now, we don't yet have the possibility to use baseline covariates, but we can still take advantage of population parameters directly in the random block and only keep the pre-block for adding the covariate models here, right? So we can define the covariate model here. For time-varying covariates, you will still have to define a pre-block. Even in the upcoming versions, we will not support time-varying covariates in the random block because the random block, by definition, is not supposed to be time-varying, whereas the pre-block is a function of time. And so if you have any time-varying covariates, then you have to use them here, even in upcoming versions. For now, you also have to use baseline covariates here, but again, that we hope to change in the near future. Okay, so this is sort of the main introduction that I wanted to discuss to these non-Gaussian random effects. But again, you can get creative with these distributions. You can define any kind of distribution in the random block, and FOCE will work just fine. Or Laplace, but FOCE is recommended. And you can define beta distributions, you can define legit normal distributions, gamma distributions, etc. And they do make sense in different contexts. And actually, if you go to the tutorials page, so let's go back to our homepage, which I can find here. So if we go to the homepage, tutorials, you will see there is one tutorial at least on non-Gaussian random effects, and it shows you when you might be interested in using a non-Gaussian random effect. For example, for bioavailability, you might want to use a beta distribution for bioavailability, and when you might be interested in using gamma distributions, and how that sometimes the gamma distribution gives you a less biased estimate than a log normal distribution in some cases for the population parameters. So it's a very interesting article that was originally, I believe, derived from some work by Andreas and then written up by Jose, who is an ex-colleague of mine. Okay, so this is rough. Again, this is like a basic introduction to non-Gaussian random effects. I mentioned you can also use non-Gaussian error models. So you can define distributions here that are not Gaussian, although this comes with the caveat that you would need now to be careful which optimization or fitting algorithm you need to use, because FOCE might not just work for all distributions that you define here. But we tested FOCE that it seems to work, or at least in theory, it has no additional restrictions on the distribution type here, and so you can change the distribution here to anything, and hopefully it works with FOCE. Good. Let's see how we're doing on time. Any questions so far? Okay. So that's it for non-Gaussian random effects. I suggest you also, if you're curious to learn more about this, to take a look at the documentation. So we have documentation on this as well that you might find also interesting. And yeah. Maybe the tutorial is also a good reference for this, but anyways. Good. So that's all for non-Gaussian random effects. And again, the goal is that it makes your or the hope is that it makes your model more readable. It gives you more flexibility, so you can define sort of appropriate distributions. If you have bioavailability, you probably want to define a beta distribution for the random effect for that. So it gives you more modeling flexibility, but it also gives you the ability to write compact models that's not too cluttered, and then also gives you the ability to write often faster models, because models that take advantage of the random block and put more parameters here and have less parameters used in the pre-block will also eventually run faster in Pumas, partly because the random block does not depend on time, but that also has implications on how we calculate gradients and allows for faster gradients to be computed. And these optimizations, they're not all there yet, so some of these are still being worked on. Okay, so this is it for non-Gaussian random effects for real. Real quick, we have the uncertainty quantification. Let's see if we have 5 minutes left. So I'm not sure if we have time to go through this. Maybe we will take an early break and come back and discuss this, because this will take a little bit of discussion. And the reason is that there are different ways to get to estimate the standard errors in Pumas, and some of them, or the one of them in particular, will fail for this model, actually, which is the asymptotic estimator. And to discuss why it fails and how to fix it in more details, we'll need a bit more than 5 minutes. So maybe we will take 5 minutes extra break and come back in 20 minutes. And we can continue after that, just to have a bit more continuity in the discussion and not interrupt it halfway. So let's keep going. So before the break, we saw how to fit a model, how to diagnose a model or plot different diagnostics, and even how to write the model in different ways, taking advantage of non-Gaussian random effects. And then we stopped right before the uncertainty in population parameters, which we will briefly cover, and then followed by simulation and prediction. And hopefully with the remaining time of today, we can talk about Bayesian estimation, perhaps briefly, but we'll see how much time we have at the end. So let's continue. So the way you can compute the standard errors in Pumas, or in general, really, not just in Pumas, is there are a few methods to do it. One common method is using something called the asymptotic estimator. And so if you're curious about the asymptotic estimator, it's described here. So if you go to the standard error estimation section in the supporting material slides, basically the way the asymptotic estimator works. So this here is just some math and notation. So that's the maximum likelihood estimate that maximizes the marginal likelihood. So this is the marginal likelihood of subject I, and that's the product of marginal likelihoods for all the subjects. And the maximizer of this is essentially the maximum likelihood estimate, which is this theta star. The way the standard estimator works is by using this formula here, which is well known in statistics, that the maximum likelihood estimate, if it's unbiased, it will generally be normally distributed, assuming that you have enough samples. Eventually, it will be normally or asymptotically normally distributed around the true parameter values and with a covariance matrix V. And the covariance matrix V is given by this matrix here, where A here is the essentially Hessian of the log likelihood. So this is the Hessian, or the second derivative of the log likelihood with respect to the population parameters, or the negative of the Hessian, actually. And this here is the score. This is often called the score outer product matrix. That's the gradient of the log likelihood with respect to the population parameters taken in outer products with itself, essentially. And so the sum of these score outer product matrices defines B, and the negative of the Hessian of the log likelihood defines A. And this is known as the sandwich estimator. It's a sandwich because it's B sandwiched between two A inverses. And actually, what's called the standard estimator is essentially this, and so often we don't actually know what the true V is here, and the true A values, or A and B, and so we actually try to estimate A and B, and the way we estimate A and B is by So if you look at this, this is actually the true asymptotic distribution, but the true asymptotic distribution requires us to evaluate these Hessians and these outer products at the unknown true parameters, which we don't know. So the idea is that we're trying to identify these true parameters, but because we don't know them, we can try to estimate these by plugging in the theta star instead of theta 0, and then we get the estimator for A, B, and A, or A inverse and B, and then we get the estimator for V, and this should be asymptotically correct in the limit as you have more and more subjects, essentially. And so this is how we compute the asymptotic estimator, is by computing A and B, first using the data that we have at the maximum likelihood estimate that came out of a fit function, and then we try to use A and B to compute this quantity here, and this gives us the covariance or the variance covariance matrix of this asymptotic distribution of the maximum likelihood estimate. And so the interpretation of this is that it's some sort of uncertainty estimation about how sure we are or how confident are we in the values of theta star. And so the idea is that if you have a few subjects, if your model is well identifiable, you should be able to get a pretty small variance or variance covariance for the maximum likelihood estimate. And if you have few data that might not help you identify your parameters very precisely, then you would have a larger variance for those parameters, or if you have a few data points or a few subjects. And so that's sort of the idea here. And one immediate problem with this is that it uses the normal distribution. And so whenever using asymptotic arguments, we always use normal distributions typically. And so, but the problem is theta could be a positive parameter or a covariance matrix, like some elements of the covariance matrix. And so theta star here includes all of the population parameters. That's all your thetas, all your sigmas, all your omegas. They're included in this theta star. And so they don't really have a support or domain from minus infinity to plus infinity. And so if your variance is large enough and the parameter value is, let's say, close to 0, then you may end up with negative values here. Let's say if you're trying to simulate from this, you may end up with some negative values. And that's a problem, essentially. And so that's why some people don't prefer the asymptotic estimator, but it is a very useful and very quick diagnostic, because you don't need to, like, the alternative would be something like Bootstrap, where you can resample your data or from your data with replacements and then refit. And that can also give you some estimate about the, or some way to quantify the uncertainty in your parameters. But this is often a lot quicker than Bootstrap. So it's a good idea to start with it, but it's perhaps not the best estimation method for standard errors in general, especially if, again, you have large variances or large standard errors and your parameters are close to 0 in their value, but they should be more than 0, like they're positive parameters. Good. And so if we take it, once we estimate this V hat, if we take the square root of the diagonal of this, those are the standard error estimates. So that's how we compute the standard error estimates from the sandwich estimator. Now, this is giving some more details about how we actually compute this efficiently using something called a generalized eigenvalue problem. It's not too important, but you can find the details here if you're interested. Now, when does this fail? Because it does fail. Actually, let's confirm that it fails. I'm pretty sure it does, but I haven't called it yet. So if I call this here, it tries to calculate the variance covariance matrix with the asymptotic estimator, and it will eventually fail. Once again, it's taken some time to compile and then to compute all these A's and B's, and then at the end it realizes that it failed, and it will terminate in a second. And so it failed. It couldn't get any standard error estimation, no confidence interval, and that is a problem because that's what we want to get. And so it says here variance covariance matrix could not be evaluated. The random effects may be over-parametrized. That's typically a reason for this, but that's like that can lead to the real problem. So the real problem here, or the more direct problem, is that you often have some like your matrix here is singular. So this A matrix that we need to invert. So if you take a look at this form here, this A matrix can be singular. And so what is the A matrix? The A matrix is this Hessian. And so when the Hessian is singular, this usually indicates that we have some identifiability issues in our model. And so it means that, or often it means that your model might be over-parameterized, and so locally there might be different like there's a continuum of parameters locally that all give you good or the same log likelihood, and so that's identifiability problems. And so let's take a look at all the possible reasons for why this could fail. So this could fail if A hat is singular, as I said, or even near singular. So sometimes it's not exactly singular, but it's close enough that when you're computing the numerical inverse, it's also failing. This can happen when you have, for example, large scale differences between your parameters. Some parameters might be very large in scale, some parameters might be very small in scale. And so even if your matrix is technically not singular and your model might be identifiable, but the scale differences can make your model near singular, which can also make it sufficiently close to being singular that the inverse operation fails. And the problem is that another problem is it could have negative eigenvalues. And this can happen if your fit did not converge to a good local optimum. And so if you look at this here, this is basically the Hessian of your objective function value, right? And so the Hessian of the objective function value, we expect it to be essentially negative definite or not singular and negative definite. And so this here should be positive definite if you actually reach a stationary point, like a local maximizer of the log likelihood. And so if your fit did not work very well or it failed, then you also could get potentially negative eigenvalues here. And so this might not be negative definite as it should. And so there are a few reasons why this might fail. And they often indicate some serious problem that you need to look at, which is why even if you don't use the standard error estimation method, this sandwich estimator method, it might still be useful to look at the output and see why it's failing and try to reason about it. And one common cause is this poor identifiability of at least one parameter. And all it takes is just one parameter to break this whole estimation. And so if you just have one parameter that couldn't be identified, then your infer function is going to fail. Or it could be that you have some significant numerical errors. And so that's often a problem. And so how do we find which parameter to might be not identifiable? You could either do trial and error. So in this case, for example, I tried to fit it so I fixed all of the omegas. So I tried to make sure the omegas are taken out of the fit. And the way I did this is by using this constant coef function. Constant coef option that allows me to fix some parameters. So some parameters should not be optimized. And when they're not optimized in the fit function, they're also excluded from the standard error estimation process. And when they get excluded, it's possible that you can actually do the estimation after that. And so here I'm also passing optim options, which is the optimization options, and I'm setting the number of iterations to 0 because I don't want to actually optimize further. I know this is a good enough solution. I'm initializing from the fitted Pumas model parameters that were obtained earlier. And so I know that these are good parameters and I don't need to optimize. So this is the equivalent of non-mem max eval equals 0. And so now I just, as a workaround or as a hack, I put constant coef here and list all of the omegas, all the omega parameters. Now, maybe not all of them are not identifiable, maybe only one of them. And I can show you another tool that can help you figure out which one. But it's technically not in scope, so we'll see. Anyways, here I'm also defining the init-randefs keyword argument, which allows me to initialize the random effects from the same empirical base estimates. Right, so I'm basically just sort of removing the omegas from the computation of infer. And if I do this and then call infer once again, you will see that it might actually not fail. And this sort of supports this hypothesis or this idea that, or rather the fact that, the infer function will fail often when you have some identifiability issues, local identifiability issues. Okay, so whenever we remove the omegas or when we remove the omegas, we see we can actually get some standard error estimates and even confidence intervals for all the other parameters, but it ignored the omegas. Now you could try to sort of play whack-a-mole game here and just remove or add back one at a time and seeing if it works. So that would be just with trial and error. Alternatively, there's actually a function in a package called optimal design. So Pumas also has optimal design of experiments as a workflow. And so if you load optimal design here, you can call a function called analyze identifiability. And this function was developed by myself and presented in the class page last year. that allows you to figure out which parameters you need to fix in order to make your model identifiable. And so once the optimal design package is loaded, but before that, you see that adding this one omega actually did not break the infer functions. That's good. And so it's likely one of these omegas. And I suspect it's probably the PD omegas, because the PD parameters tend to have identifiability issues most of the time. And so just to continue with this nice experiment, let's add back the PK parameters and see if we can get their standard errors. And indeed we can, so that's good. So we've narrowed it down to now you see this problem that I was mentioning earlier, that the omega is sufficiently close to 0 and the standard error is sufficiently large that the confidence interval includes negative numbers, which is theoretically impossible because omega can only be positive, right? And so that's the problem I was talking about earlier, that your asymptotic estimator might not be very good or very accurate when you have estimates close to 0 with standard errors also sufficiently large. And so that's the problem I was talking about earlier. Now, again, you can try these values here and see, or try adding one at a time and seeing which ones you might be the cause of the problem. Or you can try to use this analyze identifiability, which I have not tried running. So we'll see if it works for this particular model. But before we do that, let's call the help mode to figure out how to call this function, because I actually forgot. And you will see that one of the ways to call this function is by passing in a fitted Pumas model. And I can tell it to use the observed Fisher information matrix, which is the A matrix. And so let's do that. So I can pass fitted Pumas model here. I believe it's called FPM. Yes. And then I can tell it to use observed equals true. And I can pass a whole bunch of other options here, which are not necessary. PSD tolerance is how close to positive definite do I want or how close to singular do I want to allow the matrix to be? And so I'm setting it to 1e minus 6. Let's just make it a bit higher, 1e minus 5. And then let's see the output of this analyzed identifiability. Again, I have not tried running this, so it might fail, but we will see. But this is generally a good practice to inspect your model further and see if it works. So I'm getting some error, so that's probably that's not going to work. That's probably a bug that I need to fix. But let's make it equal false for now, just to see what happens. So it's taking some time because it's computing the expected Fisher information matrix rather than the observed, and it's trying to analyze the matrix and figure out essentially which rows and columns to remove from the matrix to make it identifiable, and what's the minimum number of rows and columns or parameters to fix to make the model identifiable. So that's how this function works under the hood. And it uses some nice optimization methods to do that. So now that it's finished computing the Fisher information matrix, it's running the identifiability analysis. So hopefully we should get something soon. And it's telling me that the model might be identifiable. So when that happens, I sometimes try it with a different tolerance, and it's not able to show non-identifiability in this case. Okay, so that failed. So maybe it doesn't always work, but I can look into why. And I suspect it's because we're using the expected Fisher information matrix and not the observed information matrix, which is actually the one used in the infer function call. But you can always use the trial and error method here and try to figure out which parameter exactly is causing this infer to fail. The alternative is to not use the asymptotic estimator at all. But before that, let me show you how to actually pull out the standard errors. So we called an infer function, and then we got this object here. So this object is essentially another type or an instance of a type, and the type is just a Pumas model or a fitted Pumas model inference or something like that. But it has all of the standard errors inside, but to actually get the standard errors out, you need to call the std error function on this type here, and it will pull out the standard errors. And it will either give you the, so you can get the standard errors by themselves, or you can also get a table that includes a summary of all of the coefficients. So in this case, the std error function, so if you look at type of n first, it's going to be some, again, very long nested type, but the first part of it is this fitted Pumas model inference type. And then if you call the standard error function on it, or std error, you will see that we have the standard errors here coming out as a name tuple. And if you would like to present them in a slightly better way in a table or in a data frame that you can summarize and report, you can actually have a data frame version of that with the coef table function. So this will give you the parameter name, the parameter estimate, the standard error, the relative standard error as well relative to the parameter estimate, and the confidence interval for this parameter. This is the 95% confidence interval, and you can also change that confidence interval using the level. So there's a level keyword argument that you can use to change that as well. I believe you have to pass it to infer. So you specify the level of the confidence for the confidence interval here, the confidence level for the confidence interval. Okay, so that's how you do the asymptotic estimator. Now, we haven't discussed Bootstrap. We skipped this line here. But to do Bootstrap, it's very similar. Again, we rely on the idea of multiple dispatch, where I can pass additional arguments, and the behavior of the function will change depending on the arguments that I'm passing. And so in this case, I can pass the second argument as the Bootstrap struct here. And this Bootstrap struct will take in a bunch of options, including the number of samples, for example, maybe the random number generator. So if I'm curious about this, I can go to the help mode and write Bootstrap, and then see the documentation. So I can do stratified sampling, for example, in the Bootstrap, and I can control things like the random number generation, the number of samples, etc. And so so that's the Bootstrap, and let me just go ahead and call it with 5 samples, because the fit does take a long time. Bootstrap will be generally preferred whenever you have parameters that or models that might not be very well identified. The infer function might not work very well. You might have numerical errors, etc. You might have confidence intervals outside of the bounds. In general, Bootstrap does not have these problems. But the issues with Bootstrap is very computationally expensive, and you need many samples often to get good estimates of the confidence intervals. And so it's quite a computationally heavy task. That's why maybe it's better not to start with it, but for the final standard error estimation, you probably want to do a Bootstrap. So now this will take some time to run, but then after that, I can call the std error function again on the output of infer, and this should give me the standard errors. And again, I can also call the coef table on the output, and this should give me the standard errors with the estimates in a nice table format. And so let me go ahead and also call that afterwards with the Bootstrap output of infer, just to take a look at the confidence intervals. And again, it will take a few moments because it's doing 5 fits. Essentially, it's a Bootstrap will resample with replacements from the subjects, and then it will refit the model. And the idea is that some subjects will be repeated multiple times, and some subjects will be dropped out when you do that, because you're always sampling and then replacing. But you're sampling the same size as your population. So if you have only 20 subjects in your population, you're sampling exactly 20 subjects with replacement, which means that some subjects will be repeated, some subjects will be dropped, and that causes some variability or variance in the data, and that variance in the data then propagates to the maximum likelihood estimates, because we refit every time. And we refit initializing from the output of, or the current population parameters that we used. And this could also be a problem. It could be used to, because we're always initializing from the same parameter estimates, you might be more likely to converge to local optima that are near that point. And so Bootstrap itself is not completely perfect in terms of, like, it does have its own set of limitations in that it's somewhat sensitive as well to where you initialized from. And that could also be a problem. because typically we initialize all of these bootstrap fits from the same parameter values, which might underestimate the variance a bit, just because the optimization algorithm is typically going to converge to things or solutions near the current solution and not anything that's potentially far away. But if you want something that is generally more robust for uncertainty quantification than just Bootstrap, then you want to go full MCMC and do full Bayes. And so that's one of the main sort of advantages of full Bayes, is that you have way less assumptions. You sort of avoid many of these problems with Bootstrap and with the asymptotic estimation. You respect the domains naturally, and you can also get some reliable uncertainty estimates that are not sensitive to this multimodality problem that I mentioned. In theory, if your posterior converged, it should be able to capture most of the or all of the different modes. And so even if you have multimodal behavior, it should still be fine. And so that's the advantage of going full Bayes with this. And that's what I'm going to demonstrate next. Well, after we discuss simulation and prediction, we're going to cover Bayesian estimation, which we talk, which is basically full Bayesian estimation. The reason it's called full Bayes, so while this bootstrap is running, the reason that we call this full Bayes and not just Bayesian is that actually when you maximize the marginal likelihood, this is also half Bayesian in some way. In fact, it's called empirical Bayes, and that's where the word empirical Bayes estimates comes from. And so the reason it's called empirical Bayes is because we're actually being Bayesian with respect to the random effects. And if you remember yesterday, I kept referring to the distribution of the between subject variability as the prior distribution of the random effects. And actually one way to think of these nonlinear mixed effects models is that we're actually being Bayesian with respect to the parameters of the random or the individual parameters with the random effects here by assigning a prior distribution to them. But then the prior distribution itself has some hyperparameters, have these additional parameters that are all shared between the subjects. And so each subject will have their own parameter, like they'll have their own PK underscore eta, they'll have their own lag underscore eta. Each subject has their own parameter, but the prior distribution is shared between all of the subjects, meaning the parameters or the hyperparameters of the prior is all shared. And so the question is then, what is the best prior to use? And the best prior from an objective standpoint is the one that maximizes the marginal likelihood. And the marginal likelihood is often a quantity that's used to compare models in Bayesian estimation. And so we are interested in the prior distribution that maximizes this marginal likelihood. And so when we do optimization or fitting or point estimation of the population parameters here by maximizing the marginal likelihood, but we're being Bayesian, or we assign a prior distribution with respect to the random effects, and we take into account the uncertainty, and we model the random effects or the individual parameters, we model them as random variables. This is us being Bayesian with respect to the random effects, but being frequentist with respect to, or empirical with respect to the population parameters. And that's why this whole framework is often called empirical Bayes. It's not full Bayes because we're not modeling the population parameters themselves as well as random variables. We're not assigning prior distributions on the population parameters, but we are still being Bayesian with respect to the individuals. And we can still get things like the posterior distribution of the parameters for each individual. And in fact, the empirical Bayes estimate is nothing but the mode of the posterior for each individual. And so all the Bayesian concepts sort of apply to the individual model. Even when we're not doing full Bayes, you still can apply all the Bayesian concepts to the individual model. And that's something that I realize a lot of people in pharmacometrics often don't realize, is that we are actually being Bayesian with respect to the random effects, even when we're not using full Bayes or MCMC. But enough talking maybe on the side. I think we have the bootstrap finished. So let's go back to that and take a look at the output. So the standard errors, again, as a name tuple here, and then the standard errors in a table format. And what you will see here is that the problem that we had earlier, go back, we make this a bit larger. The problem that we had earlier, that some omegas were negative in their confidence interval, is gone. So we no longer have negative confidence intervals here, which is pretty good. And so all the PK omegas have positive confidence intervals, all the PD omegas have positive confidence intervals, and so that problem is gone. And again, it worked out of the box without looking at or without failing to estimate these things, and or to estimate the standard errors. And yeah, one look at this, and you might see that maybe this omega here might be a problematic omega because it seems to be driven down to close to 0, and the standard error is even closer to 0, and the relative standard error is also quite small, and so the confidence interval is very small. And so this may have been causing numerical errors. If you remember, I said that you can also get numerical errors if your matrix is near singular but not exactly singular, because of scale differences. And so the scale of this parameter is extremely small, but then we have the scale of some other parameters like 96, and those scale differences could be causing the infer or the asymptotic estimator to fail. And so my likely suspect is this one. I think if you remove this one, because obviously it's not contributing much to the model, I can just fix it to 0 and get rid of it, then most likely the infer, or it's possible that the infer function might actually work, because the scale the scale differences will improve. Okay. So just some more insights into that. But then, of course, we only use 5 samples. So often you need to use maybe 1,000 samples, sometimes more. It's really hard to know how many samples you need to use. It depends on what you're interested in. To get good estimates of the confidence interval, you often need many samples. To get a good estimate of the standard error, sometimes so again, like to get good estimates of any kind of measure of mean or measure of centrality or any quantiles that are close to the median, you generally need less samples than to get good estimates of the tail behavior of the distribution. And so whenever you have this like 95 percentile, or this is rather the 2.5 percentile, and this is the 97.5 percentile, these percentiles will not be very accurately estimated unless you have many, many samples. And so you need to have often a lot of samples, but there is no clear rule as to how many. But I've seen people use 1,000 just because it's a good number. But there might be rules for it that I'm not aware of, to be fair. But at least, yeah, something to think about, that the number of samples of a bootstrap, how many samples are sufficient. I think you might find some papers on that. I'm not sure, but something to think about. Maybe some people here actually know this stuff more than I do, so please chime in if you do. It's getting a little bit theoretical now, so I'm sure people here have more expertise than me. Good. So I think we're done with infer. And so we also have SIR, or sampling importance resampling. So you can call the infer function with another argument here that's SIR. This also tends to work sometimes. And so but it typically requires first the asymptotic estimator to work first. And then we try to use the multivariate normal distribution. So it tries to fix this problem here, that the multivariate normal distribution might support some negative numbers, for example, but it tries to correct the multivariate normal distribution using something called importance sampling, or sampling importance resampling, or SIR. And so it works slightly better than the infer or the asymptotic estimator, but it requires that the asymptotic estimator itself actually needs to work to begin with. And so that's the problem. Then you can also pass your own multivariate Gaussian in theory, but in Pumas, I don't think we support this feature yet. If you want to pass your own proposal distribution, is what it's called, for the sampling importance resampling to work. But yeah, it's not included here, but it's be similar to this. So you just need to do call it SIR, call SIR here, and then you need to define the number of samples and then the number of resamples. But again, that will do the asymptotic estimation first, and then try to do SIR based on that. Any questions or comments? Okay. Often people unmute, and so I assume that someone has something to say, but sometimes it's just an accident. Good. So we covered inference or infer and how to get the standard errors and the confidence interval and the advantages of the different approaches. Or disadvantages. So SIR will generally be faster, for example, than Bootstrap, but it will be slower than the asymptotic estimator, and it's halfway in accuracy usually. Although Bootstrap, for it to be accurate, you need a lot of samples as well. So that's the problem. Of course, Bayesian estimation can help you remove some of the assumptions in your model and some of the assumptions in the bootstrap and the asymptotic estimation, but it also comes with a cost that the computationally Bayesian estimation or full Bayesian estimation tends to be quite expensive as well. But when you compare it, you should always compare it to the cost it takes to do a bootstrap, because Bayesian estimation gives you out of the box all of the uncertainty estimates of the parameters. And so it's equivalent to doing a regular empirical Bayes fit or maximum marginal likelihood fit, and then followed by a bootstrap, right? It's somewhat comparable to this whole process and not just to the fit part. And so when you're comparing the performance of Bayesian estimation, your target sort of benchmark should be how long does a bootstrap take after a fit and not just the fit part. But anyways, I digress, and we will cover Bayesian in more details and get to that eventually. Now, the next part, so I'm going to move to another section. So if anybody has any questions about what we just discussed, the uncertainty estimation, this is the time, because I'm about to change topics a little bit. Okay, good. So let's talk about simulation. So often a pain point in other software is that you can do maybe estimation in the software, but if you try to simulate or do some very complicated simulations, you may have to switch tools. You may have to redefine your model in some other tool and then do the simulation in this other tool. Okay, so one of the advantages with working within the Pumas framework is that you can actually do the fit and the simulation and all the uncertainty estimation and diagnostics all within one framework, and in fact even within one script that you can define. And of course you can easily save the results and load them later on with the serialization that we showed, and then continue your analysis on another day. But the nice thing is you have access to everything within the same language. And so you have access to the model here defined, you have access to the population that was read from a data frame. You can define your own population parameters here that you want to simulate from, or you can use the output from a fitted Pumas model. This could also be saved, for example, so FPM could be serialized and then deserialized or loaded, and you get the optimal coefficients out of it. And so this is so there are different ways to do simulations in general. You can do pretty much all of them in Pumas, and so let's cover a few common simulation techniques or exercises. Okay, so the first simulation exercise is to simulate a single synthetic population. So a synthetic population is just like a regular population that was observed. The difference is that the random effects are sampled, and then the data is also sampled. Then sampled the data from its distribution. And so we sample two things. We sample the random effects and we sample the data variable like the concentration and the PCA. And so this here will give us just a single synthetic population. And so if I call the simobs function, and simobs is one of our most overloaded functions with many different ways to call it. And this is, again, probably a good demonstration of this idea of multiple dispatch, where you can pass it different inputs and it has different behaviors. This puts a lot more emphasis on documentation because you need to know what the behavior is that you're getting when you call this function. And so it's always good to consult the documentation to make sure you're simulating what you think you're simulating, because again, you could call it in different ways to get different behaviors. And so when I call simobs like this with a model population or data and then parameters, I get simulation that samples the random effects from their distributions for each subject. So for each subject, we're going to use its covariates. We're going to use the background or the covariates of that subject, and then we're going to sample some random effects from the prior distribution or from the between subject variability distribution for the random effects, and then we're going to sample data from the distribution of the response. And then we summarize at the end, we just combine them in a vector. Now, if we look at the type of this here, the type of SIMS1, it is a vector of simulated observations. So again, it's just a vector, right? So just like the population was a vector of subjects, this here is a vector of this other struct called simulated observations, right? And so because it's just a vector, I can easily get the first element of it. It's called SIMS1. I can get the first element of it, and it's this simulated observations. And if I look at the visual representation of that, it's just a simulated subject, essentially. So this here is a simulated subject. Now, if I want to convert this to a regular subject that I can use for fitting, and I can use for other simulations. So there's a difference in Pumas between a simulated subject, which has a lot more intermediate variables stored in that simulated subject. So a lot of the values, for example, for the random effects used to simulate this are stored in there. And so we have more information in the simulated subject. But if you want to go back to a regular subject so that you can do more fitting or more estimation or something like that, or even more simulation, then you can call the subject function, or often this function is called a constructor because it constructs an instance of a subject struct. But this is just a function. So you can call the subject function on a specific simulation. So this is the first simulation. And then it will give you a regular Pumas subject. Now, the difference is that this Pumas subject now has new responses. So the values of concentration and the values of PCA are now simulated values and not the real values that came from the data. But the values of the covariates are still the real values that came from the data, and the values of the time points are the time points that were specified in the data. Now, if I want to change the number of time points, or if I want to sample at different time points, I can specify here which time points exactly I want to sample. And so maybe I want to sample from time of 0 to time of 10, and with a step size of 0.1, right? So this is more dense sampling perhaps. And so I can sample, let's say, from 0 to 30. And then when I do this, I will end up with many more observations for each subject. And then if I convert the first simulation to a regular subject, you'll see that now I have 301 observations for concentration and 301 observations for PCA, because now I changed the observation times. And so it's no longer using the time points that were defined in the population. It's using these time points now that I specified here. Okay, so the SimObs function is extremely powerful. You can always go to the documentation, write question mark, and then SimObs, and you will see that there are many different methods for this function, and we're adding all of these methods here, and then it's explaining how they work, etc. Yeah, always a good idea to check the documentation and the tutorials for how to use the SimObs function. But this is definitely one way to do it. And again, the ops times is one of those keyword arguments that you can pass to this function to allow simulation that's much more, let's say, like finer simulations than just the time points that were used in the data. And this is often useful if you want to plot, for example, and so you want to make predictions or simulations at finer time points to get smoother plots as opposed to raggedy plots, which you get if you only make predictions or simulations at the time points that were in your data set. Then your simulation plots and your prediction plots might not be very smooth. And so this is often used for smoothing as well. Or if you want to get things like AUC, for example, which requires a bit more finer time steps or a smaller time step to get a good estimation of things like AUC and Cmax and so on. Okay, now yesterday we covered how to handle or work with vectors, and so if I want to convert all of these into a subject, I can map the subject function on all the simulations, and I can get a vector of subjects. All of these subjects have been simulated from the SimObs function, and then now I can convert it to a vector of subjects here. Alternatively, I can use broadcasting like this, and then broadcast this, which is a bit shorter and nicer to use. And now I get, again, for each of the simulations, for each of the simulated subjects, I can convert it to a regular subject that could be used for fitting and further simulations. Okay, so that's one type of simulation. We'll see what else we can do with this besides converting it to a subject. There are many things you can do with it, like plots and other things. Yes, we will get to that. But let's say I want to sample multiple different synthetic populations. So let's say I'm doing some clinical trial simulation, and I want to maybe do multiple sort of simulations and re-estimation and figure out how the uncertainty in my model or sort of affects certain things, like certain properties, like maybe the power of the study or something like that. And so often you may want to do multiple or simulate multiple synthetic populations. And so again, we can use regular Julia syntax for this. Just call this function 100 times and you get 100 different synthetic populations. And this is one of the advantages of having access to a full programming language that you can use, which, with nice syntax, which allows you to take advantage of all these features. And so we don't need to provide a special function for this, because you can just use Julia to do that. And a lot of clinical trial simulation code will be heavily using or relying on Julia features to organize the code in different ways, to have simulations done like this in like groups of simulations and so on. And so often a lot of each clinical trial simulation, depending on what you're trying to do, you will be relying a lot on pure Julia features, mixing them with Pumas. And so you'll be using Pumas just as a regular package, but you still need to write your own simulation code on top of that. In this case, it's very simple simulation code. We're just literally running the same command 100 times. And one way to do this is to utilize this array comprehension command. And so we saw how we can do this array comprehension command, which I can use to generate a vector of values. And so this I can use it to generate, for example, all the values from 1 to 10. Right. And so I can use this syntax just instead of I'm using simobs, right? And so I'm using the actual simulation from the previous line instead of I. And because I don't care about the variable name here, I'm just using underscore, but I can also use I if I wanted to. I can use any variable, but then I'm repeating just 100 times. I'm doing this 100 times. Every time it's calling this function again. It's not just calling it once, it's calling it 100 times. And then it's combining all the outputs of the simobs calls into a single vector, right? And so that's what this is doing, and it gives us a vector of vectors. Now, let's say I want to combine these into a single, or flatten these into a single vector. Again, yesterday we saw how you can flatten a vector of vectors into a single vector by using this reduce function with the vcat. So vcat concatenates two vectors together, and so it can be used as the reduction operation in the reduce function to essentially flatten the structure. And now we have a single vector of 3,100 simulated subjects. Those are basically the 100 subjects per, or 100 scenarios, let's call these scenarios per subject. And so we had 30 subjects here, or rather 31 subjects, and then we had 100 scenarios per subject. And so the total number here is 3,100 scenarios or simulated subject. Good. Here, this talks about the ops times keyword argument, which I already mentioned, that often you might want to take more finer simulations, which is useful for plotting. So speaking of plotting, we have the simplot function, which allows us to take a look at simulations. So let's take a look at the simulations of the concentration. So it takes the output of simobs. It takes the output of simobs here, which in this case I called it find sims because it has a find time step. And then it takes also which observation you would like to plot, among other options. You can take a look at the docstring of this function for more details about what the function does. And then you can call it also for the other observation, just to take a look at how the simulations look. Yeah, that's the simplot function. Now, let's say in some cases you don't want to simulate from the random effects. Let's say you want to consider only the individualized models. So you want to use the empirical Bayes estimates for the subjects to simulate instead of using the entire population. So sometimes people do forest plots, for example, based on all sorts of these simulations. And sometimes it makes sense to use the empirical Bayes estimates to simulate, to see the behavior for each subject individually, and not just the sort of like not sample values from the random effects. And sometimes people will do this because the random effect distribution is not very well specified, or their VPC does not look very good, and they still want to make some clinical trial simulation based on their model. And so often people will be using the empirical Bayes estimates, which is actually a problem in this case because it will underestimate the variance in your model. And the proper solution is to go back and fix the model, maybe fix the random effects distribution of the model. And Lorenzo Contento here, my colleague, has some interesting work about how to do that using machine learning. So you can use machine learning to fix your random effects distribution. And he presented a webinar about this a few weeks ago. So you can go on our YouTube channel and you can find it. But I digress. Even though it's not always the best practice, depending on what you want to do, but sometimes it is what you want to do. So maybe you want to simulate future predictions, for example, and compare it to future observations, or use this to make maybe certain dosing decisions for each subject, in which case it does make sense to use the empirical Bayes estimates for those simulations. And so if that's what you want, you can pass the empirical Bayes estimates as the fourth argument. So I mentioned that we try to stick to the order of arguments here. So we always start with model, then we go with population, and then we have the parameters. And then the fourth argument can change depending on what you're trying to call. So in the case of a fit, it was FOCE, right? And in the case of a SIMOBS, you can either drop the fourth argument or you can pass the fourth argument as the empirical Bayes estimates. If you drop it, you get this case here, where you're simulating the random effects. And if you don't drop it and you pass it as the empirical Bayes estimates, then it will use the empirical Bayes estimates to simulate the observations. And so in this case, it will only sample for the response or from the distribution of the response, and it will not be sampling the random effects. So let's call this function. But otherwise, the output has the same type. And so the output here is still a simulated population is what we call it, or it's just a vector of simulated observations. So if I call again type of sims3, it's just a vector of simulated observations. So the exact same type as before. It's just that the type of simulation that we did is changing now. But everything you can do to, like the output of SIMOBS is always unified. And so anything you can do to one of these outputs, you can do to every other output of SIMOBS, including mapping it, converting it to a subject, even converting it to a data frame, which we will see in a moment. Now, one thing you might want to consider is when you're simulating, you want to make sure the random number generator is consistent every time you run your code. And the reason is not to cheat, but the reason is that you want reproducibility in your decision-making process. And so if you run the simulation and then pass the code to your colleague and they run the simulation and then you both get different results, that's not very helpful. And so sometimes it's best to set the random seed once upfront and on top of the script and do it just once. And then basically pass the random number generator. So here, this is the default random number generator that's used by Pumas. And then you can set the seed with this random.seed function. Random is a module in the standard library or a package in the standard library in Julia. And so I can use it to set the seed of this random number generator and then pass it to every function that requires a random number generator. So whether it's a bootstrap process or whether it's a simulation or sampling importance resampling. So all of these will require a random number generator to be passed. And so you can pass the default one. And the default one, even if you don't pass it, it will actually use it because it's the default one. And so you can, often it's sufficient to just put random.seed at the top. But here you can also define your own random number generator. For example, I believe one is called Merson Twister, random dots. There you go. So that's a type of random number generator that you can also define. You can pass the seed here directly. So these are different ways to define an RNG or a random number, a pseudo random number generator. Obviously, it's not a true random number generator. Okay. So why do we set the seed only once upfront? Because if you set the seed every time you're trying to call SIMOBS, you'll be getting the same sequence of random numbers. And so you could easily bias your decision making by doing that because you're basically introducing these correlations in your simulations unintentionally. Because if every time I call SIMOBS, I first set the seed, then I'm getting the exact same simulations, which introduces these additional correlations that are completely spurious and unphysical or unreal. And so you should not do that. You should try to set only the seed, preferably upfront. If you set the seed multiple times, always make sure to use a different seed and not the same seed over and over again. But in general, the best practice is to set the seed once upfront and then run the whole script with that seed. That way you get reproducibility, but without risking too much correlation or spurious correlations between your random numbers. Okay, so, and we actually have a full tutorial on that as well. So if you go to the tutorials page here, there is a tutorial on how to do simulation and setting the reproducibility when doing simulations. And so here we talk about all the different ways to set the random number generator or to define it and set the RNG. And as I said, it's a pseudo random number generator. So it's just an algorithm that tries to mimic random number generation, but it's not a true random number generator, which is why we can actually reproduce it. Okay, so again, there are many tutorials here that you might find useful. A forest plot tutorial is also here. This is not something we will touch upon in this workshop, but it is a very common plot that people ask about all the time, and so you might be interested in learning more about it. Covariate selection with backward elimination or forward selection or stepwise covariate modeling. Again, not something we will be touching too much upon here, but there are some nice tutorials about this as well. We will be getting to see more of time to event models later on, and maybe not discrete data. So if you're interested in discrete data like ordinal regression or negative the Poisson and negative binomial, then you can also take a look at this, so discrete response models. And again, there are many other useful tutorials to look at here, but I digress. So let's go back. Now, this here is, so we have the ability to call SimObs directly on the output of a fitted Pumas model. This, however, will not be simulating from the random effects. And actually, it's no longer recommended to do this. And so that's why we have this message here that we might deprecate this method. And I accidentally left it in the training material. And so I suggest we remove this and instead replace it maybe with the full version. So we have model, pop, coef, FPM, because often people used to call this, or some people assume that this would be sampling from the random effects, but actually it used the empirical Bayes estimates, which is less often what you want to do when you're doing simulations. And so that's why we sort of went ahead with deprecating this. And so it's not the recommended way to go anywhere or in general. And so if you want to use the empirical Bayes estimates, let's be more explicit and call empirical Bayes. And this is more of this is one of those trade-offs between, again, compactness and readability. Just looking at SimObs FPM, it's harder to know what it's doing here. But looking at SimObs with empirical Bayes, I can more confidently assume that it's using those empirical Bayes estimates, right? And so there is this trade-off here, but in general, verbosity is welcome if it can help readability, and it's not just getting in the way. Okay, so here I can pass the RNG or the random number generator, and the way to do this is by passing it to this option or this keyword argument in the SimObs function, and the keyword argument is called RNG, and the variable that we're passing is also called RNG. Now it doesn't have to be. We can call this RNG1, and then we can pass the variable RNG1 to the keyword argument RNG, right? And so the variable name doesn't have to match the keyword argument name. But it's usually a good idea to make them match, because if they do match, I can actually have a shortcut notation or syntax. So in Julia, if you write it like this, if you write a keyword argument like this, it will automatically expand it to RNG equals RNG. So that's a nice feature of Julia, that I don't need to explicitly say what the value is if the value or if the variable that I want to pass has the same name as the option. Then it knows to just expand it to this, right? And so that's a nice reason to make sure that the option name is the same as, or the variable name that I'm passing has the same name as the option that I'm passing it to. Otherwise, you can always do this, right? If it's called RNG1, then you can always pass it explicitly like this. But anyways, so let's run these again. And that's how you set the seed to get reproducible simulations. Now, another method of simulation that you can have, or that we use, is to simulate from the output of infer. Now, infer, as I said, is, or as we saw earlier, is what allows us to get or quantify the uncertainty in the population parameters. And because often with the fit function, you're always getting a point estimate. You're always getting specific values for the parameters, but those values might be like just relying on those values might reduce the sort of variance or bias your decision making in some ways, because sometimes there's actually a bit of a leeway in some parameter values. And so maybe the maximum likelihood estimator gave us a value of 1, but in reality, there's a pretty large confidence interval for this parameter. And if we only trust the value of 1, then that might reduce the variance in any kind of simulation that we are simulating just using this specific value. And so often what people want to do to sort of mimic a little bit the idea of Bayesian estimation is to take into account the uncertainty in the population parameters. when you're simulating. So when you're simulating, we're not just sampling the random effects and then sampling the data, but we're also sampling the parameters from some representation of uncertainty. And so we're sampling values for the population parameters. And the way we do this is with the normal distribution or with the asymptotic estimator, we sample from the normal distribution, right? So we saw the asymptotic estimator here. So we sample from this distribution, replacing theta 0 with theta star, or the maximum likelihood estimate. And so we can sample from this distribution to get values for theta star. Now, for a bootstrap, we can sample them directly from the samples of the bootstrap, the fitted parameters coming from the bootstrap. Same thing for sampling importance resampling. We can sample from the samples that we have at the end of the parameter values. And so by calling simobs on the output of infer, we can do what is potentially much more complicated in other software, which is just a one line of code in Pumas. You can use this output of infer, and you can call simobs on it. And instead of just sampling values for the random effects and the data, it also samples values for the population parameters. And I can define any kind of population or pass an additional population here for the simulation, because I may not want to simulate for the same population I use for training. So maybe I want to fit the model first using some data, and then I kept 10% of the data or something like that to for validation purposes. And so maybe I want to simulate for this additional data that was left out. And this is a common practice in machine learning, for example, is to fit your model on the majority, but not all of your data, and then keep some subjects for validation. And then you can simulate or predict for those subjects and see if the data seems to match, or if your model also seems to fit those additional subjects or not, that were not included in the fit. And this can help you detect things like overfitting, for example. But I digress. But the idea here is that you can call the same simobs function, but with different arguments. The different argument here being the output of infer, and then the population, and then you can pass the number of samples that you want, and it will give you 1,000 samples from this. And so this here, if we look at the type of sims4, it's a vector of vectors of simulated observations. So here it's actually doing 1,000 scenarios. And then for each scenario, it's sampling the entire population. And so now I can again reduce or flatten this directly with a reduced VCAT to flatten all of these scenarios. And then I end up with 31,000 scenarios or simulated subjects, 1,000 times the number of subjects, right? And again, for each of those simulations, it's sampling a new parameter value from the uncertainty estimator, let's say, of the population parameters, whatever it is. It could be the asymptotic estimator, it could be the bootstrap estimator, but it samples values from those this uncertainty estimator, and then it samples random effects, and then it samples the data to get the final simulation. And so this should give you a much more, I think, representative, let's say, or hopefully accurate measure of uncertainty in terms of how sure you are about the output or the response, given how sure you are about the population parameters themselves. Because often we're not always 100% confident in all of the population parameter values because you might have a small population and a large standard error. And so to reflect this in whatever decision-making process you're making or decision you're taking, often it's useful to take into account the uncertainty in the population parameters, not just the uncertainty in the random effects. Again, a much more probably rigorous and systematic way to do this is full Bayes. But if you don't want to go full Bayes because of any reason, then Bootstrap can also be useful for this, or might still want to simulate from uncertainty of the population parameters, even if you don't go full Bayes with that. Now, we did cover VPCs before and how to call the VPC or do a VPC plot out of a fitted Pumas model, right? So we saw how to do that earlier from a fitted Pumas model. You can also do a VPC on a bunch of simulations. So you can do the simulation first. Often the most expensive part of a VPC plot is the simulation. Especially if you have a very heavy model. Then there is quantile regression. So the quantile regression also takes some time, but the simulation tends to be the heaviest part. And often you want to maybe reuse the simulation. So you simulate and then reuse the simulation for different purposes, whether you want to calculate AUCs or you want to do a VPC or some other kind of purpose. And so in Pumas, you can actually define your simulations first and then pass the output of the simulation to this VPC function. instead of passing a fitted Pumas one. And so let's go ahead and do this. And this will give us a VPC, not just of sort of the standard VPC, but here we're actually taking into account also the uncertainty in the population parameters. So when we're comparing the distribution of the simulation to the distribution of the observation, we're not only considering the population parameters or the maximum likelihood estimates of the population parameters, we're also considering the uncertainty around those maximum likelihood estimates when generating the synthetic populations, right? And so hopefully this should be much more likely now to contain the observed variables, even if we have maybe slight model misspecifications. So it's a lot more robust now to slight model misspecifications because you take into account the parameter uncertainty or the uncertainty in the population parameters. So let's take a look at what that looks like. And here I'm doing the short version of the VPC plots. I'm not doing the full VPC plot here, so it's just the quick version of it to see the output. And yeah, you see that it looks fine, and perhaps there is less red regions than there used to be at the beginning as well. So that's something that you can note, that before we used to have, I think, a little bit more red at the beginning, but here it seems to be okay now. And you'll see that there's probably larger uncertainty bands here in general than we had before. So that's all for simulation. Let's see how we're doing on time. Any questions, by the way? Okay, so no questions. And I believe we may be able to touch upon Bayesian, but I don't know how much time we'll be able to spend. But let's talk about prediction, which is not going to take too long, and then we can switch to Bayesian. We have about 35 or 37 minutes left. So let's keep going. So the predict function is very similar to SimOps, but what it does is it allows you to get, actually one thing I forgot to mention is with simulations, you can also convert them to a data frame. So I can go to a data frame with the simulations, and I need a dot here. And so I can convert, actually I probably need to convert this one. This one here. So the data frame constructor expects a flat vector of simulations. And so I can flatten the simulations here that I did and then convert it to a data frame. And that will take some time because it's building this large data frame of 31,000 simulations. So it might take a few moments. And this data frame can then be printed, or you can subset it, in different ways. You can take it to R and do your plotting there if you really want. And so that's the idea. But converting things to data frame tends to be useful when you want to do visualization or plotting or for other purposes. Maybe do summary statistics, for example. You want to find the mean of some quantity or the standard deviation of some quantity. There are other ways to do summary statistics of simulations. And we will see one of them in a second or in a bit, probably after we discuss some Bayesian workflow stuff. But we will see how we can post-process the simulations and maybe extract the AUCs. For example, we might be interested in getting the distribution of the AUCs given all these simulations, right? So how do we do that? And how do we get the distribution of any derived quantity? Or how do we get the mean of some derived quantity or the standard deviation of some derived quantity? So all of this can be done directly using the simulation object. As you'll see, this is a pretty large data frame with 317,000 rows in this case. Okay, so we can always go to a data frame. That's something you can trust with Pumas. Okay, so we discussed how you can go from a simulation to a VPC and how to go from a simulation to a data frame. There's another function that we have in Pumas called predict. And the predict function will compute two things, the population prediction, but also the individual prediction. The population prediction will be using the mean of the or rather the median of the random effects, and will predict or take the mean value of the response variable. So whether it's concentration or PCA. And the individual prediction will be using the empirical Bayes estimates for the random effects to make the predictions. And when we do this, we can convert it to a data frame. And if you want to take a look at the names of the columns of the data frame, you will see that we have the conc-pred and conc-ipred. And actually, this is something that we also saw when we call the inspect function. So the inspect function will automatically call predict under the hood. And so often you don't really need to call this function yourself. If you just call inspect, then it should be sufficient to do that. If you only want the prediction for some reason and not the full diagnostics, then you can call the predict function yourself. Okay, again, we can convert it to a data frame, and the data frame includes all these different rows or fields that came from the data set, but it also includes the prediction columns that were added by the predict function, and includes all the random effects that were used to make the prediction, which is important because some random effects, this will be the empirical Bayes estimates, and these, if you want to reproduce these predictions later on, we need to know which random effects were used to make the predictions or make the iPreds in particular. So if I take a subset of the data frame, which again, a data frame works in many ways like a matrix in Julia. And so it's like it has rows and columns. And so I want all of the rows and I want these columns here, the columns columns ID, time, iPreds for concentration, iPreds for PCA. I can extract this and then maybe I can use this for plotting somehow. So maybe I want to plot the concentration of iPred over time or plot PCA over time and take a look at the behavior of a certain function. So this is all for prediction. The predict function is also quite rich and it has a lot of options. And so I suggest you take a look at it. It is, however, a deterministic function. So it does not accept a random number generator like the SimOps function does, because it would either use the random effects, it would set them to the median or it would set them to the empirical Bayes estimates. Both of these are deterministic quantities. And then it also gets the mean of the response variable, which is also deterministic. And so there's no need to sample anything here compared to SimOps. Good. So we have about half an hour to discuss the Bayesian workflow. We will revisit the simulations afterwards because SimOps is also used in the context of Bayesian diagnostics, where you want to do things like posterior predictive checks and prior predictive checks. And so SimOps is also used for those simulations. And so we will revisit SimOps again and also for dose selection. So we have dose selection, counterfactual simulations, so more simulations tomorrow, and dose selection given some Bayesian model. So we'll start with the Bayesian model and then show how you can do a very similar simulation with uncertainty to what we did in Bootstrap. And then based on that, you can find the best dose that maximizes a therapeutic success defined by, let's say, the AUC being between an interval, certain interval, and the Cmax being lower than a certain toxicity level. And so you can define your criteria for therapeutic success, and then based on that, use some optimization methods or just exhaustive search to find the best dose that maximizes this probability. And so we'll see how we can do all of that tomorrow. Okay, so any questions before I talk a little bit of Bayesian? Okay, so for Bayesian workflows, we have a nice paper that I and my colleagues wrote. And the paper talks about a full practitioner's guide or a complete practitioner's guide, or discusses the practitioner's guide to Bayesian inference and pharmacometrics using Pumas. And a lot of the paper here is actually about general practices and theory and intuition behind the different concepts in Bayesian. So if you have not seen any kind of Bayesian material before, and you're curious about how to use this full Bayes approach in Pumas or in pharmacometrics, even if you don't want to use Pumas, there's a nice background and intuition section at the end that you might find useful. And it discusses things like where does Bayesian statistics fall in the spectrum of these methods that we're analyzing, prior selection, how to select an appropriate prior distribution, the algorithm that we are using to get the samples from the posterior, what is the posterior to begin with, and then it talks in more details about the specific algorithm that we are using, and convergence and how to detect convergence or lack of convergence rather when it happens, and then do things like cross-validation and model selection. So it talks a little bit about the background and the intuition and the theory of Bayesian, but also it talks more about the Bayesian workflow in Pumas in particular, how to define a model, prior simulations and predictions, fitting, and so on. There's a long list of things here, including things like VPCs and simulation plots based on the posterior, like posterior plots, and getting things like the NCA parameters like AUC and Cmax from your simulations, and then using it for dose optimization. So that's what we'll cover a little bit tomorrow as well. But anyway, so this is a pretty large reference. It's a pretty big paper, 60 pages. So you might not want to read all of it in one go, but it is quite useful to come back to it as a reference every once in a while. A little bit of a caveat is that I think Pumas 2.4 was used when writing this paper. We plan to update the paper soon and push it out there, maybe publish it to a journal that will accept 60 pages in a paper, or we may have to break it down. But it's a nice reference regardless. And so once we update it to Pumas 2.6, it will have the most updated recommendations and syntax. But for now, it still provides a pretty good reference. And we also have the documentation. So let's talk about the documentation. Before I mention the documentation, though, we have a tutorial section as well. So we have a whole tutorial section on Bayesian estimation, introduction to Bayesian models, some random effects and how to define them. And so even fitting non-identifiable models. So this is a topic I was mentioning earlier. So I put out a tutorial and a video. There's a video about this that I recorded on YouTube. If you go to the Pumas AI channel, you will find a tutorial video about this. And so it talks about overparameterization, identifiability problems, and how is it that even Bootstrap doesn't save you in some of these cases when your model is not identifiable. And so a lot of interesting concepts are presented here to how to detect identifiability problems, and then how to fit these models with Bayesian or full Bayesian with MCMC. And so I also recommend going through this tutorial if you're curious about Bayesian inference. But again, we have a whole bunch of tutorials here, and then we also have a section in the documentation that let's go to resources. So if you go to our main webpage, pumas.ai, and then go to resources, it will take you to the documentation. And in the documentation, we have also Bayesian workflow. And this is largely modeled after the paper as well. So the two are kind of similar to each other. But here focuses obviously more on just the Pumas features and not necessarily on all the theory that go along with it. But yeah, this documentation section also has a lot of useful things to read, but again, it's very similar to the paper in many ways. So yeah, you can read either. Okay, so with that in mind, let's try to explain Bayesian inference in 25 minutes, which is obviously impossible. So let's at least explain the intuition behind it and maybe how to modify your model to adjust or to make it turn it into a Bayesian model. And as I said, when we say Bayesian, we really mean full Bayes, because we are already being Bayesian with respect to the random effects, as I was saying earlier. And so now we're just extending this Bayesianness to the population parameters. And we are not just modeling the individual parameters as random variables, assigning them a prior distribution with certain hyperparameters, but the hyperparameters themselves, or the population parameters themselves, are also modeled as random variables and assigned a prior distribution. Now, the most conservative way to do this is to have a prior distribution that's very non-informative, that has a large enough variance such that you're not biasing the estimation in any way. You're not imposing on it any kind of distribution. And so you can keep the prior distribution as sort of widely dispersed as possible. That's one approach, and that's sort of the most objective way to do Bayesian inference. So Bayesian is often criticized for potentially being subjective. You're incorporating priors which might not have any reasoning behind them, but to be as objective as possible while still being Bayesian to get the nice mathematical, theoretical benefits of Bayesian, or really of probability theory and MCMC, you can still use a prior, but make it a widely dispersed prior. That way, you're not really biasing the estimation that much or almost at all, but you can still at least define a certain domain. So at the very least, the distribution should have the correct domain. And so if the population parameter for clearance is guaranteed to be positive or is required to be positive, I need that the prior distribution also have the support of positive numbers only. And so at least the distribution, even if it's very widely dispersed, should have the correct domain, should have the correct support. And so if, again, this parameter is positive, the distribution should be something like log normal or truncated normal with a lower bound of 0, or perhaps gamma distribution. So any distribution that has a positive support or non-negative support, at least. Same thing with any other, again, population parameter that we expect to be positive. Now, if a parameter is expected to be between minus infinity and plus infinity, then I can use a normal distribution for that, unless I have a good reason to maybe prefer, like to have maybe a fat tail. If I want to have a slightly fat tail, I can use a t distribution. If I want to have the distribution skewed one way or the other, then there are other distributions that also have support from minus infinity to plus infinity, while supporting skewed behavior. And actually, one of the in the documentation for Bayesian, there was a nice plot that might be useful to show here. So this is the probability density function of many distributions. And so you'll see that from minus infinity to plus infinity, you have many of these distributions here that you can use. And if you zoom in, you'll see the names here. And then for positive distributions or positive quantities, you have a bunch of other distributions which you can use. And then for any distributions with support between 0 and 1, so if your parameter is a bioavailability parameter, then it needs to be between 0 and 1, then you can use a beta distribution or a logit normal distribution or a uniform distribution for the prior if you want to be completely sort of non-informative about the value. Or not completely, but at least in this parameterization, it's not informative about the value of the population parameter in this specific parameterization. So you're assigning the same probability to each value between 0 and 1, or the same probability density. So yeah, so we have all these different distributions with all these fun PDF curves that you can pick from, right? And of course, you have to have a good reason to pick one of those. And often a first thing to look at is, again, the support. That's usually the first thing that you want to look at. What is the support of my distribution? And that should be the same as the domain. So if this is a positive parameter, you want a distribution with a positive support. Support meaning the random numbers that come out of this distribution are all going to be positive or guaranteed to be positive. Now, the next thing you want to look at is the center of the distribution. So do I have a good reason to assume that the center has a specific value or not? And so sometimes you may have, for example, you know that roughly it's going to be around 0.1. It's not going to be, let's say, 1,000. It's not going to be like the exactly like 0 or 10 to the power minus 6. But it's going to be maybe somewhere around 0.1. It might be slightly higher, slightly lower, but picking a center for the distribution is often the next challenge. And one way we can do this is just like so what I did here, I took the same initial value of the parameter. So when you initialize the parameter in a regular Pumas model, you can take that same value and use it as the center. Because if you have a good reason to initialize the parameter at this value, then you probably have a good reason to think that this value here is close enough to the center of to the reasonable values of this parameter. And so that the goal of the prior distribution is to capture the set of reasonable values for a parameter, right? It's not supposed to sort of inform or be sort of heavily informed by the data. So you're not supposed to look at the data first and then look at the prior or try to define a prior based on the data. So it's not supposed to be heavily informed by the data, but it's supposed to represent the plausible set of values that your parameter can take. And if your parameter can take values that are from 0 to 1 million, then your prior distribution should reflect that, the fact that your parameter can take values as widely dispersed as this. And that's the next challenge. So beside picking a center for the distribution, which in this case, in the log normal distribution, the center is the mean or the median of the log scale. So this here is the median of the log scale. And so the median of the parameter was 0.134, or we're assuming that the median of the parameter is 0.134. 0.134, and so the log of that parameter or the log scale median will be log of 0.134. And so you always have to be careful with these log changes, because the first argument or the first parameter of a log normal distribution is not the mean of the log, or is not the median of the log normal distribution, but it's the median of the log scale. And so if it was just the median of the log normal, we can just use this, right? But it's actually the median in log scale, and so we need to pass log here first, or call log first. But anyways, we mentioned that you first need to worry about the support of the distribution, and then about the center of the distribution. And then third, but not least, is the dispersion of the distribution. So how would you, or how dispersed, or how certain or uncertain about the value of this parameter? So am I super confident that it's going to be around 0.134, or do I want to allow maybe a few orders of magnitude difference? And so maybe I want to make this a 10, because this is standard deviation in log scale, right? And so this would actually give me maybe like, let's say 3. This would give me a few orders of magnitude difference, that it can go up or down a couple of orders of magnitude, or a bit more actually, if you consider plus or minus 2 standard deviations. But the idea is that you're giving it more flexibility. You're saying that all of these values are plausible values, and all of them are likely to be the true parameter value. And so the idea of the prior, again, is to represent your belief about what the value of the parameter may be. Before observing any data, you think the parameter may be taking these values, and so you find the distribution that represents this. Now, often people will also be using a prior distribution because they want to use information from a previous study. And so another approach is, instead of trying to be as non-informative as possible, is to actually embrace this process of being able to include domain knowledge, or your own sort of information that might be obtained from some other study. And so often, for example, in pediatric analysis, you have an adult study that's already been conducted, and then your model corrects for allometric scaling, but then the parameter values have already been estimated for the adult study. And so you already have some idea about what the parameters may be, because the parameter values have been estimated from the adult study. And you also have standard errors for those parameters from the adult study. And so you can take those parameter estimates and the standard errors and try to find an appropriate distribution that is inspired or taken from that adult study or that previous study that used a different data set, but maybe you don't have access to the data set anymore, and you only have access to the parameters and the standard errors. And so if you only have access to the parameter estimates and the standard errors from a previous study, you can use them to dictate or define an appropriate prior distribution, because you suspect that this study would not be much different from the previous one. Now, you can still make your standard deviation a bit more widely dispersed. And so if the standard error was, or of the log scale was something like 0.1, so maybe you can make it something like 0.5 or 1, just to give it a bit more dispersion, allow for more shift between, like, maybe the pediatric population has different population parameters than the adult population. So allow some more sort of change to happen between the two studies. So maybe you want to increase that standard deviation a bit. But this will be another approach, is to embrace the informativeness of the prior distribution and try to actually have a good source or a good reason to define these priors based on previous studies, right? So one way is to be as non-informative as you can, only define the distribution that captures the plausible values of the parameter before observing any data. And typically that just means you have a good support, or the support is correct, and you have some center that's sometimes arbitrary, like if it's positive, the center can be 1, and then you have a large standard deviation or dispersion parameter for the distribution. So typically that's how people try to build these largely non-informative priors. But then also you can build informative priors based on previous studies if you actually want to take advantage of a previous study to maybe reduce the sample size in a pediatric study. And so that's another application of the Bayesian approach, is that you can combine prior knowledge or prior information from another study and incorporate it together with the data coming in from a new study to be able to more sort of estimate the parameter values with more certainty and with a smaller sample size. And so that's the idea, that you can reduce the sample size and still be able to get a lower uncertainty or low uncertainty for the parameters. Now, of course, if your prior is misspecified or is contradicting with the data, there's always a risk of that. And so that's why you should always try to test and check with different priors and see if I change the prior, if I make the prior weaker, does my conclusion or my decision that I take, does it change significantly? And if your decision is very sensitive to the prior choice, then often that means that you need to pay extra care or justify a bit more your choice of prior, or even check if your prior might even be contradicting your data. And if it is, then that's a problem. And so I actually, in the paper, I go through the different scenarios of prior distribution. So let's go back here real quick. So I have a whole table here that discusses when you can sort of abuse Bayesian estimation. So Bayesian estimation can be abused, and if you define a prior that's too strong that says the drug works no matter what, and then the drug effect has a prior that basically guarantees you always have a drug effect in the posterior, then you will end up with obviously you're basically cheating in that case. So that's sort of like in this case, you have no scientific basis for the prior. It's super strong, it's informative, but it contradicts the data, right? The data says the drug doesn't work, but your prior says it works. And so your posterior will still say it works. And that's cheating. And so that's the reason for some people are often careful with Bayesian and criticize it for being subjective, is that it has that potential that if you misuse it, you could potentially cheat, which is bad. And even if your prior so yeah, so I go through all the cases here, and if you want to define an informative prior. So if you want to define an informative prior, it gives you a lot of power, but with great power comes great responsibility. So you need to also be careful how you use this informativeness of the prior. But a safer option most of the time is to try and opt for a non-informative prior and just use it to give you the benefits of Bayesian inference and the benefits of probability theory and MCMC to replace Bootstrap, for example, without necessarily getting into this whole area of how exactly to select a prior distribution, and try to hope or try to aim for having a prior distribution that's not very sensitive, that doesn't affect your conclusion that much. And so if you make it twice as weak, you get the same conclusion roughly at the end. And so aim for this lack of sensitivity of whatever decision you have at the end relative to your prior distribution. That's if you want to be as non-informative as possible. Such that, again, the prior shouldn't affect that much your decision, but it still helps to use Bayesian because it has some nice mathematical properties. Okay, so I talked a bit about the prior distribution and the role of the prior. So let's go through the main changes that we need to do to a Pumas model to turn it into a Bayesian model. And really the only change that you need is to define a prior distribution here instead of a domain. And that's it. Technically, you can still define a domain. So you can still define a sort of real domain here instead of a prior. But this goes into a field called improper priors. And so it's not recommended. So I would always suggest defining even a very loosely informative or very widely dispersed prior over defining an open domain for the parameter. But it would still work in a lot of cases, even if you just define a domain for the parameter without a proper prior distribution. Good. One thing that we also use here is this constrained multivariate normal, which works just like a regular, or rather a truncated multivariate normal. So this is a truncated multivariate normal distribution with a lower bound of 0. The main difference between this and truncated multivariate normals is that we don't need to compute the sort of renormalization constant. So if you're familiar with how truncation works, you try to compute the area under the curve of the truncated region, or rather of the region that was not truncated, and then you use it to correct the PDF value. But when we're defining a prior distribution in the param block, we actually don't have to be exact in computing the probability density function. And so it's a bit more optimized because it doesn't actually compute the full log probability density function, but it drops some constants because this constant is difficult to compute or takes time to compute, but is not necessary when you're doing Bayesian estimation. And so this is just like again, like a truncated normal distribution. But the nice advantage of this as well is that you can actually have a covariance matrix here if you want. In this case, we're using this additional method of the multivariate normal. So remember, the multivariate normal distribution is part of the distributions of JL package. and we can define it outside. And so this here is just the syntax for saying that this is the mean of the three random variables that are normally distributed, and my standard deviation is 1. I believe this is the standard deviation. Yes. So the covariance matrix now, or the variance, has become 4. And so the second argument here, when it's just a number, it's the standard deviation of the different random numbers here. Now I could have also just done like this 2 times, or rather 4 times the identity, and that would also work, right? And so here it's the covariance matrix, which is just 4 times the identity matrix. This is the identity matrix of size 3 by 3. So yeah, so there are different ways, different methods to define the multivariate normal distribution. You can see all of them. If you go to the help mode, $MV normal, you'll see all the different ways to define a multivariate normal distribution here. And you can use any of them inside this param block. Okay, so we're using this constrained multivariate normal distribution for the omegas. If your omega is a matrix, you would need to use something like inverse Wishart distribution or a Wishart distribution. Or if you want to break it down to standard deviations and correlations, and we also talk about how to do that. So often a better parametrization is to break down the covariance matrix into a correlation matrix and then the standard deviations. Then you can use the LKJ prior for the correlation, and then you can use the any kind of positive support prior for the standard deviations. Right, so we have different ways to define these priors depending on how you want to parameterize your model. But again, we don't have that much time to go through Bayesian in this workshop. If you're interested in a dedicated Bayesian workshop, we sometimes offer those as well. So you can shoot us an email and we can try to arrange for something like that. If you're interested in a full workshop on Bayesian, we gave it once before in ACOM, and it was a success. Good. So with the standard deviation parameters, they need to be positive. And so again, we can use this constrained normal distribution. Alternatively, we can use log normal, right? You can use gamma. So you can use any kind of positive distribution or positive support distribution. And that's about it. So this is everything you need to do in order to turn your model now into Bayesian. And the rest of the model is the exact same way. It has not changed at all. Now, next, I show here how to modify the fit function to make it do MCMC. And so first of all, let's talk about differential equation solvers. And so in this model here, the differential equation that we have, because we have this nonlinear function of CP, it's a nonlinear ODE. And it's nonlinear in so the rates of change here, especially this rate of change, is a nonlinear function of the states. And this means that there is no tractable or easy analytic solution for this, and we actually have to use an ODE solver. Now, the ODE solver will typically start from, let's say, time equals 0 in the initial value, and then it will take some time steps to try to simulate essentially moving the time forward one small time step at a time. And there are many different ODE solvers that have different techniques and tricks, choosing the time step such that if you have very quick dynamics happening, you want your time step to be smaller. If you have very slow dynamics, you can use larger time steps. So to try and balance accuracy with speed. And so one nice and ODE solver that's recommended by our in-house ODE guru, Chris Rakokas, is this RODAS 5P algorithm that we often use, especially with Bayesian estimation. You might need to use this, or whenever you suspect that your dynamical system might get a bit wild. And the reason why things get a bit wild with Bayesian estimation is that often if your prior here is very widely dispersed, to properly explore the full posterior, if your priors here are all non-informative, to properly explore the full posterior, you will need to try, or the MCMC sampler will be trying some very crazy values for these parameters. And so very large, very small values for these parameters that are still within the support, but they might still be quite large or quite small, leading to some numerical instabilities. And so often we end up with a lot of so-called stiff ODEs. So stiff ODEs is a concept or is a terminology that's used to refer to ODEs that may have some slow dynamics in some part with respect to some states, fast dynamics with in some other time points with respect to some other states. And so you have this idea of varying speeds in the dynamics. And so you need to adapt the step size accordingly, depending on which part of the simulation you're in. And the problem is that it's hard to predict when an ODE solver is going to be stiff and when it's not. And so we have some heuristics inside of Pumas to do an auto switching or sort of figure out when the ODE might be stiff and then switch to a stiff solver. But sometimes with Bayesian, it's better to just switch directly to this, which tends to be quite robust for stiff ODEs and produces less numerical errors. And so if you ever have to, if you ever do a fit and you get some numerical errors in dynamics, one thing to always try first is to try changing the ODE solver using this option here, diffq options equal this name tuple. So this is a name tuple with an algorithm that's defined as RODAS 5b. So you can take a closer look at the syntax, but we only have 4 minutes. I'm going to briefly explain what the parameters here are, and then I'm going to end and probably we can discuss the rest tomorrow. But again, the call to the fit function here is very similar to the previous call. We pass the model as the first argument. We pass the data or the population as the second argument. We pass the initial parameters, which in this case, it will just be taken as the mean or the median of the distributions. They will be taken as the initial parameters. And then we can call this Bayes MCMC or define this Bayes MCMC structs here because it's just a demonstration. I'm not using a lot of samples, but I'm using only 200 samples with 100 of them being adaptation. If you want to know more about these options and what they mean, you can revisit the paper and it will have more details about what these options are actually doing. And then I'm sampling 4 chains. So 4 chains meaning I'm just running the sample or this sampling procedure 4 different times. And each time it might give you a different set of posterior samples. And so the goal here is to sample from the posterior distribution of the population parameters and the random effects simultaneously. So we're trying to sample from the joint posterior of the population parameters and the random effects of all the subjects simultaneously. And again, we produce 4 chains here. Each has 200 samples, the first 100 of which are the adaptation samples. If you ever use TAN, you're probably familiar with many of these terminology. Now, another option that's not recommended in practice, but just for speed to demonstrate this running faster, is you can change something called the max depth of the tree in the so-called NUTS algorithm or no U-turn sampler algorithm. And this is generally, again, not recommended if you want to get better convergence to the posterior, but just for performance, I am reducing it here to demonstrate this faster. Now I can run this and hope that it finishes in time. But let me make sure I didn't modify anything in the model. I think, I believe I did not. And I think with this, I can conclude and let's just watch the sampling. And tomorrow I will start from here again and explain what the sampling does in some more details and perhaps even revisit the idea of a posterior. I realized I jumped over that a bit too quickly if you're not familiar with what a posterior is. So we can revisit some of those discussions and concepts tomorrow.